Ladies and gentlemen, welcome to Aspen HYSYS workshop. Kindly be reminded you are required to install the Aspen HYSYS software before the workshop. Besides, please mute your microphone when you are not speaking to prevent any disruption. Please take note that this whole session will be recorded. Lastly, please be ready as we will start our session shortly. Thank you. A very good morning I bid to our respected speaker, Mr. Teo Wei Jian, and everyone attending this Aspen HYSYS workshop organized by UTP IKE. I am Winnie, and it is my pleasure to be your MC for this workshop. For your information, this session will be covering the basics of Aspen HYSYS and a case study, which will help fellow participants to have a better understanding about Aspen HYSYS. To start off, please allow me to introduce our speaker. Today, we are going to have Mr. Teo Wee Jian, an on-site operations engineer at LinkedIn, involved in the operation of a separation and steam methane reforming plants. Besides, he is also an Aspen certified expert user in Aspen HYSYS and has received various accolades and achievements. During the pandemic, he has volunteered as community teaching assistant for MIT's Principles of Manufacturing MicroMasters. Therefore, it is our honor to have Mr. Teo here to share about the Aspen HYSYS. Before starting the workshop, please be informed that if you have any question and wish to ask the speaker during the session, you may post it in the chat box or open your mic directly to ask the question. Without further delay, I would like to welcome Mr. Teo to start his sharing. Please welcome.
All right, thank you, Winnie. So, can you hear me?
Yes, we can hear you.
Okay. Sorry, can you hear me again?
Yeah, sure.
Okay, sure. Then I'll use this. All right, thank you, Winnie, for the kind introduction, and let's get started, shall we? So today we are going to be looking at learning Aspen HYSYS basics in the next 3.5 hours. All right, and so let's get started on what we have today. So I'm going to talk a bit of myself, some common myths about Aspen HYSYS, the basic usage of Aspen HYSYS, and some hands-on examples. So it's best if you have your own copy of Aspen HYSYS so that you can follow along and you know what's happening in the slides. It's a little bit more about myself. I'm a part-time engineer, coffee enthusiast, so to say. I have a YouTube channel where I post like stuff about Python and VBA. I was once involved in UniChat, which is an app that you can download from App Store and Google Play. I have some small awards that nobody cares about. My interests are in mostly AI, coding, simulation, and automation. And that's why I like to do things in an automatic way and not manually. So a little bit about my university life. So I was once offered a site visit to an offshore platform. I can be joined a few times the National Chemical Engineering Symposium involved in UniChat, as previously mentioned. I also helped to organize hackathons, conferences, and just to mix it up, a Chinese literature competition. So what do I do now? So I'm I sort of moderate the platform called Chemical Engineering IR 4.0, which is a Facebook group and Telegram group where people discuss stuff related to chemical engineering. And there are usually a lot of the Aspen Plus and HYSYS questions in there. So you can feel free to join if you're interested. It's always open. I also frequently post things on LinkedIn. So if you're interested in like looking at the nonsense that I post, feel free to follow me on LinkedIn. But before we start, right, I've talked to you about what I like and what my interests are. So I would like to know what your interests are. Like, what is your favorite chemical engineering subject? And there are quite a lot of choices here. So can you please post the poll and let our audience like fill in. Okay, so I see the poll is up. So let me know what your favorite or least favorite chemical. Let me know what your favorite chemical engineering subject is. Okay, I see the top votes here are mass and energy balances, separation processes, and fluid mechanics. That's actually interesting because I don't really like fluid mechanics, for example. So someone, okay, so there's like quite equal balance between subjects here. That's good. Okay, so you can continue voting in the background, but I'm just going to continue with the slides. So I see that like most people are like quite okay with mass and energy balances, separation, heat transfer, fluid mechanics, process control. Even someone said subject out of chemical engineering. Okay, that's not good. But anyway, let's proceed. Oh, someone likes process simulation. Okay, that's good to know. All right, so let's continue. Before we start doing something, it's always best to know what we are doing, right? It's always best to be actually understand why we do something. So what is process simulation? Process simulation is part of process design, but it is not exactly process design. So in outside, you might hear a lot of people saying, oh, process design, process simulation is the same thing. It's actually not the same thing. The importance of process simulation is I want to represent a chemical process by a flow sheet. So flow sheet is something like this. This is a flow sheet. And this flow sheet shows the major operations in your chemical process. All right, so that's what a flow sheet is. And each flow sheet block consists of a mathematical operation. So for example, in this flow sheet here, let's get my pen up. There is a mixer here, for example, and this is where the feed comes in. So the first is acetic acid, and the second is acetylene. So this is a mathematical operation. Basically, the process simulator does a mass balance to calculate the stream after the mixing, which is called S1 in this one, in this screenshot. And then next, it goes into a heater. So there is also a mathematical operation here, which is Q equals to MC delta T, which is a heat transfer equation. In order to calculate the heat required, so you need some kind of heat input at the site, and also to calculate the outside temperature. And then in the reactor, you also have a mathematical operation where we convert some part of the feed into the product, and there might also be a heat change because of the heat of reaction. Same thing with cooler, same thing with the separator, which is also a mass balance. So you can see that there's a mass balance recycle, and then there is a product stream. So basically, to put it very simply, a process simulation simply represents a process in a series of mathematical operations. So these are the mathematical operations. We have mass balance here. We have heat transfer. We have reaction engineering. Just put RE. We have heat transfer. And we have separation. And the reason why I asked you guys about your favorite chemical engineering subjects is that you will need the theory or at least a knowledge of each operation in order to actually simulate something so that you understand what you're doing. All right. So let's go back here. And we have covered the first 3 points. The next is steady state versus dynamic simulations exist. So this is a more advanced concept. But the simple way to put it is that whatever we are doing is called steady state. Whatever we are doing now in this workshop is called steady state, where we have some input, we want an output. That's it. All right. However, there's also a more advanced kind of simulation called dynamic simulation. For example, I want to track a unit operation when I start up the plant. So temperature rises. I want to see how the product changes when the temperature rises in a reactor, for example. You can do that, but it is much more time consuming and it also needs more inputs to process. So today we are also going to focus on steady state. So don't think too much yet about the dynamic simulations. So from a process simulation, we can get mass balance, which is the most basic concept of chemical engineering. We can have energy balance. It's the second most basic concept of chemical engineering. We can have equipment sizing, which is needed to actually buy the equipment to install in the plant itself. You can get power and utility consumption, which is required to get the operating costs of some plant that I want to build. And finally, the costing. So the equipment sizing, which will be the capital costs. And then the operating costs will also be factored in to get the overall cost of the project. And then we can know that whether this plant is worth it to build or not. So maybe it's not worth it, then maybe we look for a different process to build. So this is an example of a flow sheet. And this example is, I would say, quite simplified because it doesn't have the actual intricacies of the process. So for example, this vinyl acetate production process can be expanded to a more detailed process. So for example, we have this recycle loop. The recycle loop goes back into the feed here. And we also have, so like in this previous flow sheet, we only represent it as a mixer. It's not as simple, right? After that, we have a heater. So maybe due to some considerations, we cannot just have one heater. We need to have multiple heaters. So in this case, you can see that they are actually a series of 3 heaters. And then there's some heat recovery, heat integration to save energy. All right. And then we have the reactor. And then because that reactor maybe it's an exothermic reaction, it creates heat. So we have like 2 coolers. So again, there's some heat recovery here. So maybe the feed is preheated before it actually enters the reactor. So that's very common in the real process. And then we have the separator. And maybe because this separator is, one separator is not enough to produce the required separation. So we have 2 separators. And this separator perhaps need a lower temperature. So we have a cooling between the separators. And then we have the 2 distillation columns to produce the required product. So a real process does have a lot of intricacies, but usually what you do, the easy way, is to start with this, and then slowly add in the required unit operations one by one. So start with a simple one. Make sure you can get the results. Make sure that you look at the product is correct, the waste is correct, before you go into the details. Don't try to start with the detail. You will get very confusing. Right? So that's how usually we go about doing a process simulation. So you might have heard also about the term called process synthesis. And then you're wondering, why are so many terms in process simulation? The fact is that process simulation is, I want to know what this process produces when I already have the process. I have a process, but I don't know what it can produce. So I put this whole process into the simulator. I see what is the output. That is a process simulation. Process synthesis is usually what you do in your design project or your final year project. What you do is, I have a product. I need to think how to produce that product. That is called a process synthesis. So you might be thinking, if that's the case, right, am I joining the wrong class? Because what I'm doing seems to be process synthesis and not simulation, right? Because I have a product I want to produce and I want to think of how to do it. In real life, process synthesis and simulation, they work hand in hand. So first, I will start with some product. Okay, I know I want to produce product X. I think of how to produce that product. I sketch out maybe on a piece of paper about what reactor I need, what heat exchanger I need, what distillation column I need. And then I put that into HYSYS, which is the simulation part. And then I look at the result. Is the result what I want? If yes, then it ends. Okay, that is my final simulation flow sheet. Then I can use it, submit to my lecturer, or I can continue the steps. But usually what happens is that we cannot get the result we want. So we go back to the simulation and we change some parameters. Then we check again. If it still doesn't match the result we want, go back to the simulation, check the parameters again. So this process repeats. However, if I iterate quite a few times, I still cannot get the result I want. Maybe there's something wrong at the start. Maybe I have put in the wrong unit operation. This is supposed to be a stripping column, but I have simulated it as a distillation column. It cannot be done. So I will then go back to the synthesis phase. And then go through the simulation process again, check the results, iterate with the simulation, and so on, until you get the flow sheet which produces the result you want. So that's how process synthesis works with simulation. And that's why even though you are doing a design project, you need to do simulation. So that's how it goes. In the plant design concept, right, we don't just jump into designing the plant. So this is sort of a very high level overview about what happens from a product being invented in a lab to the product being produced in a real plant. So from top to bottom, this can be 20 years, 25 years minimum. All right. So first, some scientists or some chemists will invented this product in the lab. Oh, we can produce this product. This is a new kind of plastic. This is a new kind of polymer. This is a new kind of bioplastic, biodegradable plastic, for example. Okay, so then this scientist publishes a paper on some journal saying, oh, this plastic is a new material that can be used. Then the next phase will be conceptual process design, which is to think of how to produce that plastic in a real scale. Because in a lab, it's very different. You mix reagents together in a beaker or something, and then you get it. In real life, you can't just mix that in the beaker. You need to have a process. All right. And then this goes through maybe some iterations. So maybe test it out in the lab scale, whether this process works. And then you go to a pilot plant, which is like a small plant built in real life, in real conditions, to see whether this process works and whether we need to think about any other considerations that we need to think about. And then there's an iteration process here again until we get the result that we want. So usually this is like 5 to 10 years. It's usually like 5 to 10 years. And once we have the pilot plant works, okay, this product can be produced in real life, not just in the lab. We jump into the next phase, which is the engineering, procurement, construction phase. And this phase, this term is called scale up, meaning that we scale up from pilot scale to commercial scale. The first thing to do will be commercial evaluation, which is like, is there a market for this product? Do you want to like really produce it and sell it? Because a product that is good in the lab might not necessarily be commercially viable in real life. Maybe it's too expensive to produce. So after someone decides, okay, this company X wants to produce this product, we go into basic engineering design phase, which is to come up with the PFD, which is the process flow diagram, the PNID, the piping and instrument diagram, and then we come up with the like basic plant layout, how the plant is going to be look like, and so on. Then we go on to what we call front-end engineering design, which is where we flesh out all the equipment in the plant. For example, we need to have this reactor. What's the sizing of this reactor? 5 meters diameter, 10 meters tall. You have this distillation column. How tall is it? You have this vessel. How big is it? You have this pump. How much power that it needs, and so on. After that, it will go to the detailed design phase where we actually come up with the details of each equipment. For example, this pump. What is the flow rate? What is the head, pump head? What is the manufacturer? What is the motor? What is the voltage supplied to the motor? What is the power requirement? We come up with very detailed information about each equipment in the plant. And then we buy the equipment. We order the equipment, maybe from China, from US, from Europe, whatever. Then we put them in the plant. We install them inside the actual plant, the site. And then finally, we go to commissioning, which is like we start up the actual plant. And this usually takes about 5 years. Usually take about 5 years, maybe shortest, maybe 3 years, 3 to 5 years minimum. And finally, we operate the plant until, for example, the plant is too old or the product is obsolete. And the operation phase can be 20 to 30 years. So that's how the whole process works. And you can see that your plant design is going to stick around for a very long time. So if your design, your process design is a conceptual phase, it's going to stick around for like 30 years at least. So there are a lot of things, there are a lot of factors that to be considered when starting a process design. All right. So that's how it looks like in the whole industry. And maybe that's a bit too big to be discussed today. So we just go small scale and see what we can do using process simulation. So if we are designing a new process, we can do conceptual design, which is like trying out which process works and which process doesn't. we can use that to do a feasibility study, which is to see like maybe is the cost worth it? Can we sell the product for more than it costs to produce the product, right? Alternative study. So maybe we have three different processes to produce this product. Which one is the best? And cost benefit. So maybe from that three processes, we calculate the cost, we calculate the selling price, and then we see which one gives the highest benefit. Okay. Then we can have once a new plant design, once everything is sorted out, we can have process design, which is an upgrade of the conceptual design, preliminary costing, so that from each equipment, we can get the sizing of the equipment, and then we can start to get prices for this equipment. We can optimize the process before we actually build it, because it's easier to optimize the process before you build it than only after you have built the plant, right? Because you don't have to change things. You haven't bought the equipment yet. You can at least make changes before we put down the order for the equipment. If your equipment is already bought and you find out that it's not suitable, then you already paid for it. Maybe it's like a few $100,000 for equipment wasted. And finally, you can run case studies. So for example, if something happens, if the feed changes, what will happen to the plant? So that's a case studies. So if you are in the existing plant, you still use process simulators. You can still do optimization. You can still do debottlenecking. Debottlenecking means that can I increase the production of this plant? Find out what is limiting the production. Can I make more product than what I'm having now? And then finally, case studies. Same thing. All right. So there are many process simulators out in the market actually. So I've listed like 5 more common ones and like 5 more obscure ones. So the 5 most common ones will be Aspen HYSYS, which is actually the most common process simulator in the world, according to some surveys, right? Which is owned by aspentech. And aspentech also owns Aspen Plus, which is another product of aspentech. Some competitors of aspentech will be ChemCAD by Chem Stations. So ChemCAD is actually easier to use, but has not so many features. And then we have Proto, which is usually used in oil and gas companies. And we have gproms, which is by Siemens, and it's usually more for like dynamic kind of simulations. So the top 5 are the like common ones, and the bottom 5 are the more uncommon ones. So someone, I think a lecturer from Portugal, right? He made an open source process simulator called DWSim. So you can actually download it for free and install it on your laptop. Because if you're like using Aspen HYSYS now on your laptop, but you don't realize that actually in real life, process simulators are very expensive. For example, one license, right, for Aspen HYSYS is something around the range of maybe $30,000 per year. $30,000 per year for an Aspen HYSYS license in a real company. Of course, for universities, they actually give you a cheaper price. So DWSim is completely free, and it is quite similar to Aspen HYSYS. So if you know HYSYS, you can use DWSim. So it's like quite similar. And for some more sort of specialized kind of process simulators, we have ICON, which is developed by Petronas Group Technical Solutions, or Petronas GTS. So if you have people working in Petronas, then you will probably have heard of this term, ICON. And this is a Petronas sort of like Petronas proprietary software, which only they have and only they are using. I'm not sure if any other people are using. Schlumberger has Symmetry, which is actually not originally owned by Schlumberger. It's actually owned by another company that Schlumberger bought over. And it's more on upstream applications. So for downstream applications, I try not to use Symmetry. Honeywell Unisim Design. So this is very similar to HYSYS. And finally, you have a HSC Chemistry by Autotech, which is specialized for like mining applications. So if you are mining kind of process or metallurgy kind of process, for example, you are trying to extract iron from iron ore from the earth, this is the best software for you. Don't use Aspen HYSYS. All right. So how do you select the correct simulator? So I have now, maybe I'm a student in the final year. I want to do my plant design project. How do I select my simulator? In real life, right, the first consideration is usually cost, which is the cheapest. But for student, there's no cost consideration. You just use whatever that you can get on your hands on, right? So the next thing will be application. Each simulator is designed for a certain application. For example, HYSYS is specialized for oil and gas, for refining, and some petrochemicals. Emphasis on some, only some. If you try to use HYSYS for something that is not designed for, like I have a palm oil process, can I use HYSYS? The answer is you can, but your life will be 10 times more difficult. If I have a biochemical process, can I use HYSYS? The answer is probably not, because HYSYS does not have the data for many of the components that you will use. So you need to make sure that you choose the correct simulator at the start before you even start doing your project. You don't want to be like, the design project might be something like 2 semesters long. You don't want to be doing something until the second semester, the end of the semester, you realize that your simulator is actually not suitable for the process. And then you don't have time to redo everything anymore. So it's best that you put in some effort to determine which simulator is the best for your application before you choose, right? Because if you have chosen it, you are committed already for your whole design project. So Pro 2, or the name should be Pro/2, if I'm following the name, it's also for oil and gas and refining. But Pro 2 has a weakness, is that it does not have reactor models. So if I have a reactor, I need to program in the equations myself. So that's the bad thing about Pro 2. But the good thing is that you can have a lot of customization. So like if your reactor is something that is like very unique, you can do it in Pro 2. So Aspen Plus is specialized for petrochemicals and chemicals. So usually if you try HYSYS and it doesn't work for your process, you just go to Aspen Plus or ChemCAD. This is sort of like more common ones, alternatives to HYSYS. And I would really recommend you not to use HYSYS if you are not in oil and gas or refining. If it's not oil and gas or refining, don't use HYSYS. That's the easiest way. So Aspen Plus supports oleochemicals, palm oil, chemicals, electrolyzers, for example, that you might be using. ChemCAD is quite similar to Aspen Plus in application, but ChemCAD has more like solid handling. So if in case your process has some solid powder that you need to do something to it, ChemCAD might be better than Aspen Plus. And if you are like doing some biochemical process, wastewater process, membrane separation process, find out what are the specialized simulators, because the ones in the list probably won't work. They will not work for you. All right. And also, if you have a consideration, find out whether you need a steady state versus dynamics. So 99.9% of the time, your simulation will be steady state. It's very rare if you need dynamics. So usually we just go for steady state. So for steady state, all the simulators above will support. For dynamics, you need to choose between Aspen HYSYS Dynamics or Pro 2 or Aspen Plus Dynamics. That's probably the top products in the market. All right. So tip 0. So I call it tip 0 because this is the tip before you start. Select the right simulator early on. Selecting the wrong simulator can have unintended consequences later on. For example, you don't have this component in HYSYS, which is very common. So these are some steps to start a simulation. But I'm not going through too much in detail because actually you know most of that after going through the case study. The first is to decide what components you have. So maybe you have nitrogen, hydrogen, methane, water. You define all these components. Then you choose the thermodynamic model. All right, you choose the thermodynamic model. After that, you draw in the unit models. You draw in your pumps, your heat exchangers, your separators, your reactors. Then you connect streams to them. So this is an inlet, outlet, inlet, outlet. Then you run the simulation. And then you check the results. So it's actually quite simple if you think about it. But it is actually like programming the unit operations itself that is the most difficult part in any process simulation. So I'm going to call up second poll, which is your most hated chemical engineering subject. All right. So let me just go back to my poll, and I'm going to switch the poll to the second one. Okay. So use the same link and let me know what is your most hated chemical engineering subject. Heat transfer, really? Thermodynamics, heat transfer. Hopefully no one hates process simulation, otherwise I am not sure why you're here. Thermodynamics. Okay, thermodynamics is a bit most hated. Heat transfer. Okay, heat transfer. I would say heat transfer is quite fun to me. So I'm not sure. Maybe that's just your personal preference. Okay, fluid mechanics. Okay, fluid mechanics. Okay, it seems that we have heat transfer, fluid mechanics, thermodynamics. Fluid mechanics the first. Interesting. Fluid mechanics. Wow. Okay. All right, thanks. I see most of you have voted. All right, so you can keep voting in the background if you want to. But it is a bit worrying that you guys tell me you guys don't like heat transfer and thermodynamics because you are going to use a lot of it. All right. So in this poll question, like the most, you are going to use mass and energy balance in every unit operation. You will use heat transfer for heat exchanges. You will use thermodynamics for like stream properties. You use separation processes for like distillation columns, exhaustion columns, sweeping columns, and such. Whereas fluid mechanics might be a bit useful for certain pressure drop applications, but it's a bit rare. And the rest, you can forget about them. All right. Maybe a simulation. That's what you're doing now. So it's a bit worrying, but no worries. No worries. We can go ahead. Right. So introduction to Aspen HYSYS. So we talk about process simulators in general. We talk about what are the process simulators available in the market. So let's look at Aspen HYSYS in detail, right? So Aspen HYSYS was developed by a Canadian company called Hippotech in 1996, probably like slightly older than most of you guys. And it is bought over by aspentech in 2002. So at that point in time, aspentech already has their own software called Aspen Plus, and they bought this software from Hippotech. They actually bought over the whole company and it comes with the software. So aspentech is an American company, a United States company. In the US, you are not allowed to have a monopoly in the market in what they call antitrust law, right? So you cannot monopolize the market. So when aspentech buys up Aspen HYSYS, which is the biggest player in the market, the US government says, no, you can't do that. So the US Federal Trade Commission, which is like the body that looks after these monopolies, forced aspentech to sell off their HYSYS code to Honeywell. So aspentech has been forced to sell off their HYSYS code to Honeywell. And Honeywell used this code to produce Unisim in 2004. So if you ever use Unisim, right, you realize that it looks almost exactly like HYSYS. I mean, like older versions of HYSYS. So you're wondering why Unisim looks like HYSYS. So this is the story behind. And the good thing is that if you know how to use HYSYS, you also know how to use Unisim because they are very, very similar because they actually come from the same company in the start. And HYSYS is specialized for upstream, midstream, and downstream processes in oil and gas. So mostly in refining, but they can also do some upstream and midstream processes. All right. So this is an interesting thing about Aspen HYSYS and so like how HYSYS came about to be today. So they wouldn't manage to have a monopoly. They got fined by the US government. They were forced to release the HYSYS code to Honeywell, and that's how you get Honeywell Unisim. So HYSYS is specialized for, I would say, oil and gas and LNG, liquefied natural gas applications. Any other than that, don't use HYSYS. You probably can't. With some smaller applications in chemicals and pharmaceuticals. So there are a lot of oil and gas processes here. I'm not going to read all of them, right? But I'll just highlight a few. So in upstream processes, you can do backflow and hydraulics, which is like you want to know how much the pressure drops after like maybe you're trying to build a pipeline, gas pipeline across Europe, for example, and you want to see how much the pressure drops after 10 kilometers of the pipeline. The reason you want to know is that you want to buy a pump, you want to install a pump to bring up the pressure, counter the pressure drop. So HYSYS can calculate that for you. You can also have a flare analysis, which is like if you want to build a flare, you can calculate how big is the flare required and so on. You can also do safety analysis like pressure relief valves. You want to know what kind of pressure relief valve is required, how big is it, and so on. For midstream process, which is here, the examples are mostly for LNG. It is a lot regarding the LNG plant processes. So liquefied natural gas or LNG comes out from the ground. It needs to be compressed. So you can know how big your compressor, how much power is required for the compression. Then LNG from coming out from the ground has a lot of water in it. So you have to remove the water. Otherwise, when it goes to the liquefaction process, the water will freeze and damage your piping. So you have to take out the water. And usually we do that by putting in alcohol such as ethylene glycol, diethylene glycol to take out the water from the gas. We also have acid gas removal. So natural gas naturally has some acid gases: carbon dioxide, CO2, hydrogen sulfide, H2S, sulfur dioxide, SO2, and so on. So you have to take them out before we send the natural gas to your customers. Otherwise, like if you're cooking at home, you don't want like hydrogen sulfide to be inside your home. Otherwise, it will smell very badly. And after we take out this hydrogen sulfide, sulfur dioxide, we can recover this sulfur and sell them as a byproduct. Then you can get some money back from them. So that's the sulfur recovery process. Or the naming will be the clause process, clause of Santa Claus, the clause in Santa Claus. Then you have the other parts of the plant itself. You can still do pipe flow, hydraulic analysis, you can do flare, you can do safety. Downstream process is mostly for refining in the refinery to produce fuels, to produce naphtha, to produce jet fuel, to produce diesel, and so on. So we still have acid gas removal, we still have sulfur recovery, we have crude distillation, where you separate the components of crude oil into the fractions. So we have petroleum gas, LPG, we have jet fuel, petrol, diesel, naphtha, and so on. And then the bottom you get bitumen, wax, and so on. And the same tree applies. Finally, some other more sort of like general applications of HYSYS. You can use HYSYS for property estimation. So I want to know the density of this component at this temperature and pressure. You can run HYSYS and do it. Environmental analysis, you can do that. You can measure what is your CO2 emissions. You can measure what is your pollutant, what kind of pollution you're producing, and so on. Safety analysis, same as previous, and then economics. All right. So HYSYS is quite a powerful tool with a lot of different applications, but it's quite specialized for oil and gas and LNG applications. So if it's not, then you might not be able to use it. So we need to know what are the advantages and the limitations of HYSYS, right? So the advantage is it's very specialized for hydrocarbon systems, which means that it has a lot of data regarding hydrocarbons. It supports crude oil analysis and petroleum fractions. So there are some kinds of situations where we don't know exactly what components in this stream are. But we know certain properties of the streams. For example, I want to do a distillation of crude oil. But how do I define the components? Crude oil changes from place to place and time to time. So Aspen HYSYS is able to do what we call pseudo components, or like fake components, so that you can have a crude oil as a component, as a stream in your process. Aspen Plus, for example, will not be able to do that. And petroleum fractions, for example, petrol, diesel, kerosene, jet fuel, which is also cannot be represented by just one component or just one substance. And HYSYS can do that automatically for us. HYSYS can also integrate well with other Aspen products like Aspen Energy Analyzer for heat integration, exchanger design and rating for very detailed heat exchanger design. You want to, for example, a shell and tube, you want to know how many tubes are there, how many shell buses, how many tube buses, how many baffles, how long is it, what are the supports required. You can do that everything. You can do everything in the exchanger design, everything. Aspen economics analyzer, you can come up with the capital cost of the plant. Flare system analyzer, so that you can know how much material goes to the flare and so on. Aspen dynamics for startup, shutdown plants. So disadvantage of this Aspen HYSYS is specialized for hydrocarbon system. So it's advantage, it's also a disadvantage if you are not using a hydrocarbon system. Only as good as input data. HYSYS is not smart enough to know if your data is wrong. It will just blindly simulate whatever you put in. Lack of properties for non-hydrocarbon components. So sometimes some components you can select in HYSYS, but actually HYSYS has no data on that component. So, for example, sodium hydroxide. You can put that as a component in HYSYS, but actually HYSYS does not have a lot of data on that component. And even worse is that some components just doesn't exist. For example, if you are an oleochemical process, you have something like maybe, let's say, lauric acid or palmitic acid, and they're trying to make some oleochemical, maybe biodiesel, for example, from these acids. You can't do that because the acids do not exist in HYSYS. Right? So in process simulation, I would say two items are the key. The first item is to know the thermodynamics of your process, because you need to choose it. You have to choose the correct thermodynamic model. In HYSYS, they call that fluid package, but generally we just call thermodynamic model. Using the same thermodynamic model, using different process, even using different software, the result should not differ by 5%. Usually around 1 to 2%, but less than 5%. If your result differ more than that, there is something wrong in your simulation. So that's usually like the standard that we hold ourselves to. And you do need to have some basic knowledge of what are thermodynamic models before you choose. Otherwise, you won't know what to choose, right? And you can't just use ideal guess. You can't just assume everything is ideal guess. You have very, very inaccurate results. In oil and gas applications, the most common equation of state, which is a type of thermodynamic model, is what we call the Peng-Robinson model. Peng and Robinson are the inventors of this model. The second is the Swarth-Wheatridge-Kwong model, or SRK model. So usually people just call it PR, SRK. So when you're solving some thermodynamics problem and your temperature is slightly different, don't panic, because it's sometimes just an issue of the calculation method used by the simulator. But it should not differ too far. So let's say if one simulator gives you 150, the other 147, is actually acceptable. It's still within this range, right? So don't panic if your friend gets another result and you don't. It is still within the acceptable range. So these are the two most common equation of states in or thermodynamic models used in HYSYS. The first is the Peng-Robinson model. The second is the SRK or Swarth-Wheatridge-Kwong model. So what exactly is this model, you ask me? Maybe you have not taken thermodynamics as a subject and you're asking, what exactly is this model? So basically what this model does is that this is the model actually. The first equation here is the model. And what this model does is that I want to know what is the volume of something at certain temperature and pressure. That's it. That is what the model tells me. Substitute in P, substitute in T, get V. That's what the model does. And that's putting it very simply, because you can see this equation is actually very difficult to solve. So that's why we need a process simulator to solve the model. So why do we need the volume? Because with the pressure, temperature, and volume, these three, we can choose two to provide, and the third will be calculated by the simulator. And from these three properties, we can calculate everything else. We can calculate enthalpy, entropy, density, viscosity, heat transfer, work done, and so on. So basically, you need to input usually temperature and pressure, but it can also be vapor fraction, because vapor fraction will determine the temperature and pressure. And when you do that, HYSYS or any simulator will input the data that it has already stored in the simulator, which is in this case the TC, PC, and this omega for this component. Let's say water, then HYSYS will find out water. What are the 3 parameters for water? Put into this equation, calculate A, calculate B, then you give it P and T, and then it comes out with the volume. So this is our output that I want. So to put it very simply, this is what a process simulator does. After it gets this value, you can calculate everything else. Density, molar volume, viscosity, enthalpy, entropy, heat capacity, heat transfer, work done, and so on. So to the most basic, this is what a simulator does. But in order to ensure the simulator does the correct thing, I mentioned that we need some inputs. We need the component parameters, the TC, critical temperature, PC, critical pressure, and omega, which is what we call the eccentric factor or eccentricity. You must ensure that these inputs are correct. Otherwise, you get the wrong answers. And this is a term that in IT, they call it garbage in, garbage out, or GIGO. It means that if you put garbage into the computer prints out garbage for you. And that also applies in process simulation. So before you do anything, it's best to sketch out on paper and make sure that you know the overall picture before we start doing the simulation. So I'm just going to show you this very simple thing that, let's say I'm a student, I'm trying to do this simulation. All right, I want to know what is the distillate flow rate, what is the bottom flow rate. Sounds simple, right? I have a given feed is 100 kilomole per hour, 50% propane, C3H8, 50% by mole, butane, C4H10. And the specification that I want is to have 99% recovery of propane at D, which is distillate. So I want 99% of the propane to come to the top. 90% of purity of propane at D. So I want the purity to be 90%, which is this one. And let's assume that the simulator has calculated the required thermodynamics, and it tells me that at these conditions, at a certain P, the distillate is 90% propane and 10% butane. So that's what I can get under these conditions. And let's see if the simulator can solve this problem. All right, so the purity spec is already here. So I already have the purity spec. So purity spec is correct. 90% purity at D. Okay, I want 99% recovery of propane at D. So we can first calculate out the input. So we have feed of 100 kilomole per hour, 50% of propane. So we have 50 kilomole per hour of propane. We also have 50 kilomole per hour of butane. I want 99% of this to go here. So you can use a calculator and press run, and then you get 49.5 kilomole per hour of propane. So this is a unit kilomole per hour. And then this is a 10% purity, 10% mole fraction. So you can calculate that, and that will mean that in theory, I will need 49.5 times 1/9. That means that this will be 5.5 kilomole per hour of C4. So because there are only 2 outlet streams, right? One is not going out the top, needs to go down the bottom. So it's, let me just press calculator now. So we have a remaining propane. So we have 50 kilomole per hour inlet, 49.5 going out the top. So 0.5 kilomole per hour at the bottom. It's a spacing mass balance, by the way, it equals out there. And there's no generation, no accumulation, no consumption. So C4 is 50, here is 5.5, so remaining will be 44.5 kilomole per hour of C4. So from here, we can calculate the percentage, the composition of the product. So 0.5 over 44.5 is 1%, 1.12 more percent. And the remaining with that would be 98.9%. So you can see that, but the thermodynamics say the best I can achieve is this 10%, 90%. But in order to achieve both of these items, I will need to have this separation, very, very perfect, almost perfect separation, 99% between the bottom. So this spec will be unachievable. And you can do it opposite way by assuming that this is achievable, and you can find that this is not achievable. So this is infeasible specs. To get a feasible result, we will have to either sacrifice the recovery or sacrifice the purity. And that this example alone will illustrate most of the problems that you will face when you do simulation, because the requirements that you ask the simulator to do are too strict. You can only achieve one of them. So maybe I had to drop my recovery to 95%, for example. Or if I want 99% recovery, I might have to drop the purity to 85%. And then we can get the result that is logical. So this shows that you have to sketch out the results on paper before you start doing. Otherwise, you don't realize that, and then get very frustrated. Oh, I can't get the result I want. A lot of errors and so on. And in fact, it's actually from the start, this simulation is already impossible to conduct because the specification is not logical. So it's always good to have a big picture view before you do anything. Okay, so we go on to the first case study for today. So it's at 10 a.m. So let's move on to the first case study. We'll start with a simple exercise, which is to select the chemical components and select the thermodynamic model in the process. All right. So let's assume that we have someone named Dave. So Dave is going to be our main character today. He works at some refinery. You can imagine that he works in Petronas or Shell or whatever, right? And due to refinery expansion, so maybe like after COVID, air travel starts picking up, people start driving more, there are more goods and services being bought. So there's more demand for like petrol, diesel, jet fuel, and so on. So this company decides that he wants to expand their refinery to produce more of these products, produce more petrol, produce more diesel, produce more jet fuel, because people are starting to travel more. So Dave is in charge of installing this new utility water line. So Dave is in charge of installing a new line because maybe this operation needs, this refinery has some operations that need water, and the current water supply is not enough. So he needs to install a new utility water line, but Dave needs some physical properties of this water stream, which he doesn't know how to get. So let's see if HYSYS can help us, right, to do this. To fully define the stream, we need one out of two component flow rate combinations. So I want to define one stream in the simulator. I need to know the flow rate of the component, and I need to know 2 out of 3 physical properties, which is either temperature, pressure, or vapor pressure. But usually we just go for temperature and pressure. All right. So let's try to do that in HYSYS. I'm going to just stop sharing my camera a while, just to save some bandwidth. And I'm going to switch over to my HYSYS screen. Okay, let me just open HYSYS now. So it takes some time. Okay, so we have HYSYS on my screen. So can you guys just make sure you guys can see my HYSYS screen? Because my resolution is set very high, so maybe it might be too small for you to see. So please let me know in the chat if you can see my screen. Yeah, and make sure you can read the words. So let me know if you can see in the chat. So when you first open HYSYS, you see this. You see this. So I just create a new case. So there are actually some templates that you can do. For example, a reformer in a refinery. hydrocracking unit in the refinery, residue hydroprocessing unit, fluid catalytic converter. So these are very, very specialized for refinery applications. Sulfur recovery unit also in the refinery. But I'm just going to create a new case by clicking on this. And just wait a while until it shows up. So this is how HYSYS will look like at the start. Completely empty, nothing at all. And you should jump to your component list. So the first thing I want you guys to realize is that HYSYS is very helpful in telling you what errors are there. So on this bottom corner of the screen, let me just switch to screen sharing so that you can see the my cursor. So HYSYS is very helpful in telling you what are the errors that it has, but it doesn't tell you how to solve the error. That's the problem. All right. So there's a messages pane here, and this messages pane tells us that we need to require information fluid package, require information component. You look at my slide. That is exactly what I told you to do just now. Select chemical component, select thermodynamic model. So that's exactly the basics that you have to do to make sure that your HYSYS works. So we are going to add, first we go for the components. So on the left-hand side sidebar, there is a component list. I'll click on this, click on that, and then search for the component name. So in this case, there's water, or you can just type H2O, which is a code for water, and then you just click on add. And that's it. The status changes to OK. So OK, that's done. You can add any more components if you like, but there's really no point because we are just trying to get the properties of water in this demonstration. So if I new component, say I want to add methane, CH4. Oh no, it doesn't detect this. Let me just type the name methane. And then I can just add or I click on and double click on this. That's it. You want to remove? Just click on here. Okay, so that's water. Done. So the error message for the component disappears, and now we see fluid package is the next error. Select property package. And on the left side, you see there is a fluid package button, and there's a red color symbol, and then it says under specified, which means that we need to provide more information for the fluid package. So I click on fluid package here. I click on add, and it asks me to select a property package. So there are a lot of different property packages in HYSYS. We have acid gas specialized. We have some specialized for steam, for example. But the most common two property packages in a refining application would be the Peng Robinson or the Suave Reddish Quang, which is SRK. So I'm just going to pick Peng Robinson here. And then when I click on that, the status here says OK, which means that we have already given the correct information that we require. And the error message disappears. So, okay, that means that we have already specified everything that's required in the first part. Now we can actually enter the HYSYS simulator itself. So let's enter the HYSYS simulation. What we do is from the left side, you click on simulation. And then it calls out the main flow sheet, which is currently empty because I haven't added anything. And you will see this is a basically where we play around, we add items and stuff. So there's a model palette here. This model palette is where I add the items into the flow sheet. So now I won't add any like equipment or unit operations or whatnot. I'll just add in a stream. So I'll just, from these streams, right, there are two colors, red and blue and red. Or in case you're colorblind, the left one is the material and the right one is the energy stream. So I'm going to add in one material stream. Click on once, drop on the flow sheet. So the stream is named 1, and it's a light blue in color. So I'm going to drop a second stream. That's stream number 2. and I'm going to double click on the first stream to specify the stream itself. So you can see that like a window pops up. And here on yellow, in yellow it shows a warning, which means a warning. Unknown composition, which means that HYSYS doesn't know what this stream consists of. So I'm going to just put in the stream properties. Let's say I want water at room conditions, 25 degrees Celsius. So I click on this temperature and type 25 and press enter. And when this happens, right, you see this is still unknown compositions. The reason being that vapor fraction, temperature, pressure, I need to choose 2 out of 3. I need to fill in at least 2 out of 3. So let me just fill in pressure as a second item. I want the pressure to be atmospheric pressure. So the current unit here is kilopascal. I can fill in by just typing the atmospheric pressure, which is 101, 101325, 101.325 Pascal, kilopascal. Or I can just type in 1. And in this unit, I change it to ATM. It will automatically do the unit conversions for me. So that's it. I have specified the physical property part of the stream. Now I need to specify the composition part of this stream. So on this worksheet here, move to composition, and you see the mode fraction here is empty. Click on edit. So you can choose a composition basis. We either can give the total flow plus the mole fractions or mass fractions, or we can directly give the flow of each component. So in this case, I'm just going to click on mass flow. The unit is kilogram per hour. I'm going to put in 100. Then I press OK. So now this stream is completely specified, and the status button changes to OK. So that means that this stream is completed. If I close this stream material, I find that stream 1 has changed color into dark blue, and stream 2 will still remain as light blue or cyan. So the light blue coloring means that the stream is completely specified, and then I don't need to do anything else with it. I can proceed with other things in the simulation. So HYSYS uses color a lot to tell you things. All right. So in this case, I was trying to check the physical properties of this stream. So what I do is I double click again on 1. In worksheet, I click on properties. And here I can see all the properties that are calculated by HYSYS. For example, density, volume flow rate, enthalpy, heat capacity. Let's see what we have here. Heat capacity ratio. We have kinematic viscosity, we have dynamic viscosity, and so on. So that is what the simulator does for us by solving the thermodynamic model that we specified. All right. So in this case, actually, we are trying to get the density. So density is like 1007. And HYSYS operates on a real-time kind of mode. That means, or I can call it what you see is what you get, which means that I can go back, change this temperature to, let's say, 50 degrees, press enter. The property will update immediately. So you can see the density changes because water expands when it gets hotter. I can change the pressure to 1013 kilopascal, which is about 10 atm. The properties change immediately. The density drops some more, just a little bit. So because HYSYS is a real-time process simulator, there's no need to compile, no need to run. It will run automatically once changes are done. But sometimes you don't want it to do that because it might take some time for it to run. So what do I do is I go to here solver on the menu bar. I click on hold solver, or I switch it to on hold mode. Then when I change anything, HYSYS will not react yet. HYSYS will not react yet. But if I click back on active, HYSYS will then solve the stream. So this is a very useful hack in case you have a lot of things that you want to change, and you don't want HYSYS to keep changing, updating every time you change anything, because it will take a very long time sometimes if your stream is very, very complicated. So we just put on hold, change everything. Once it's completed, only I activate the solver. So that's what happens here. Okay, so we have gotten the physical property that we want from HYSYS. All right. Let's go back and see what else Dave wants to do. Okay, so we are now in case study. Actually, one, not really case study 2 yet, case study 1B, refining blocks. So Dave's colleague, so we have some other guy called Pons who works in the same refinery. He tells Dave that this water, this 100 kilograms per hour of water, is to be used as water to a boiler to generate steam. So before this water, so this is a photo of a boiler, which is equipment that produces steam for use in any plant. And before this water can enter the boiler, this water needs to be pumped to 20 bar gauge, and heated to 105 degrees Celsius. So this is what Pons tells Dave to do, right? And now Dave wants to know, because it seems that we need a new pump. We have to purchase a new pump and install in the refinery. We have to purchase a heat exchanger and install in the refinery. I want to know what kind of pump to buy. I want to know what kind of heat exchanger I need. So there are two requirements that Pons wants us to do. The first is to know how much heat is required for the process, since Pons needs to know how much heating steam will be made. So maybe that this heat exchanger is a steam operated heat exchanger. And the second thing is about the pump sizing. So let's go and see if we can pump this water to 20 bar gauge and heat to 105 degrees. So let's do item 2A. Okay, so we now back in our HYSYS. I'll just delete this stream tool since I'm not going to use it anymore. And I'll just rename it. I can double click on it. On the stream name, I can type in, let's say, utility water. By the way, this is not Aspen Plus, so there's no limitation on the length of the name. You can type as long a name as you want. Right? And if Aspen Plus, you can limit to like, I think 8 characters. So now first I want to pump this utility water from atmospheric pressure to 20 bar gauge. So I go back to the model palette. I look for the symbol of the pump, which is actually this. If you cannot find it, go on the side to pressure changer, because a pump changes the pressure of the stream. Right? Click on pump, and you can see the pump here. So there are other pressure changes like control valve, relief valve, compressor, expander. So I'll just put the pump here, drop it on the flow sheet. Then you can see that this pump is colored red, which means that it has no connections. We need to give it some connections. Right? So how do we do the connections? Go up to the flow sheet, tap on the menu, click on attach. This will turn on the attach object mode. Hover over the utility water, click and hold, and drag to the pump inlet, which has a small blue box. Then release. Then you can see that we have connected the utility water to the pump. But the pump still is in red color because we don't have an outlet for the pump. Basic mass balance, you must have inlet, you must have outlet. So I'm going to add a second string to the flow sheet. Just drop it here. And then connect to the outlet string. And then we have successfully done the connections. So I'm just going to drag this up here, and then I'll just call it maybe like pump water. And I'm going to just activate the solver. Okay, so we still have not specified what should the pump do, right? What should the pump do? The inlet outlet, that's not enough. I still need to tell the pump what should it do, right? So I will double click on the pump, and it shows the equipment equipment screen for the pump. You can choose the inlet, you can choose the outlet, you can give it a name, you can give it energy stream you want to, but this is optional. And what we need to select here requires energy stream. Okay, sorry, we will need to draw an energy stream. So I'll just drop energy stream here. Just call it like pump work done. And then I can manually attach that to the pump, or I can just double click on the pump here. Choose it from the energy stream. This will auto attach the energy stream to the pump. So because the pump requires a power input or work done or work input. And you can see that this pump has now changed color to gray, which means that it is specified, but it has a yellow outline, which means a warning that it is not solved, not calculated, because it's missing some information to calculate. So what do I do is I double click on it, and you can see the status here is yellow, unknown duty, because it doesn't know how much power to draw, because it doesn't know what it's actually supposed to be doing. So we can click on parameters on the left bar of the design tab, and we can fill in one out of the three, just one out of the three. The first is called delta P, which is how much pressure I want to increase. The second is the pressure ratio, which is outlet over inlet pressure. And the third is the duty, which is the work done. That means I can give it a specified work done, and then it will calculate the outlet itself. So in this case, right, I want the pressure to be 20 bar gauge at the outlet. So I'll just put in delta P should be in bar, and I'll just put in 20 bar. So the pump is now fully specified. The yellow warning has disappeared, and we can now check the results. So to look at every stream going into any equipment, you click on worksheet. This will show all the equipment, all the streams that go in and out of this equipment. So you can see that the calculated pressure is 21,000 kPa. You can see temperature goes up a little because when you compress water, the water heats up a little bit in what you call adiabatic compression. Mass flow remains the same. And yeah, I can see the rest of the details. But what I want to know is actually how much power does a pump consume? So what do we do? We can click on the rating. This rating site is for more like details of the pump. But if you just want to know like what are the results from this pump, right? Just click on the performance tab. And usually the performance tab gives you the results for any equipment that you're interested in. You can see the total power is 0.07 kilowatt. So that's a power required. So let me just make this flow a bit bigger because this is a bit not realistic. So let me just give it 10,000 kilograms per hour, which is like 10 meter cube per hour, which is a more realistic number. And you can see that this pump power now increases 100 times to 7.3 kilowatt, which is actually quite a small pump. So we can buy this pump, install in a refinery, and then we can get the required pressures. So this is for the pump. Now I will go to the second unit operation, which is the heat exchanger, which we're going to heat the water to 105 degrees. So we go back to the model palette, click on heat transfer, we find the heater, we drag to the flow sheet, click on here, attach to the inlet, which is on the left side of the unit. And then I add an outlet for the pump. Then I add a heat input into the heat exchanger. So similarly to the material stream, right? For energy stream, if it is not specified, you get a purple color. If it's specified, you get a more reddish brown kind of purple. So let me just look at attachments. I'll just drag here. So inlet is on the top for a heater. And I just drag here. So this pump has all the required connections. Now I'll just specify it. Double click. Worksheet. I'll just change this name to heated water to boiler. then this will be a water heater, let's call it like heat duty. Okay, so for heat exchanger, we need to specify two things, not just the outlet pressure. The first thing is the delta P, which is the pressure drop. Because when a fluid flows through a heat exchanger, the heat exchanger has many turns, many like bends in it, and that will create a pressure drop. So in this case, I'm just going to ignore that by typing 0. And now the pressure drop has been specified. Now we need to go to where actually what the heat exchanger is designed for, which is how much heat to put into the water. Again, you can specify the delta T, which is how much you want to increase the temperature of this water. Or you can specify a duty, which is how much heat I want to put into the heat exchanger. And then the HYSYS will calculate what is the outlet temperature. So in this case, the water enters at 25 degrees. I want it to be 105. So I just put the 80-degree increase. And you can see the HYSYS has calculated for us. The heat duty, the heat required is 3.47 million kilojoules per hour. So that is the result. You can click on performance, and it shows you the heat profiles inside the equipment. But in this case, it's not that important because we just want to know the heat duty that is required for the process. So we now have a very, very simple process with two blocks. And we have successfully changed the properties of this water by pumping it to 20 bar and heating it to 105. So let's have a look again at this worksheet. We find that this pressure is actually not exactly 20 bar gauge because I have specified the delta P as 2000 kPa. So another way I could specify this equipment is to just not specify here. And you can see once I delete the delta P, the solver goes back to underspecified mode because it's not missing the information. But I can go straight into the worksheet and specify the outlet pressure. So this indirectly will also specify the pump pressure difference. So when I do that, HYSYS will calculate the required delta P, which is 1897. Same thing also with the heat exchanger. We just close this. I want the outlet temperature to be exactly 105, so it's not 105.2. So I go to parameters, I delete the delta T. So it's now underspecified, unknown duty, to worksheet, given the temperature here, 105 degrees Celsius. And that will also specify the delta T required, which is 79.83 degrees Celsius. So HYSYS is a bit more flexible in terms that it knows how to indirectly get the information that it needs without you like having to tell it openly that this is the requirement for each unit. So I can rearrange this a little, select all of them, hold shift, select more items. If I click on align selected icons, then it will align everything in a straight line. But sometimes it's not exactly straight, so I just drag this a little bit. And I can like move these labels around by click on the equipment, right click, move size label, then I can shift the label away to make the whole flow sheet look better. So this is how we start a simple flow sheet in HYSYS. And so we have already specified everything. So let's go back to the slide, right? And so maybe Dave has already done what Bonds requested from him, but how do we present that to the audience? For example, I want to just show the audience everything regarding this flow sheet. I just want to see everything at a glance, right? I don't want to like open this, look at the work done. I don't want to open this and look at the heat duty. It's a bit inconvenient for me. So what I can do is add what we call a stream table that shows everything that is all the streams that are in the process flow sheet. So what I'm going to do is go to any empty space right click on it, add workbook table. And here, it gets you choose whether you want material streams, composition, energy streams. So I'm going to just select the first one. Click on select. And a table pops up showing all the streams that are present in this worksheet. And you can actually just copy this to Excel or Microsoft Word or anything. And you can just export it. So I can also add a new workbook table, compositions. So it shows like what each stream is comprised of. So in this case, just water, nothing much. And you can add workbook table, energy streams. So this energy stream table will show the two required information that I wanted, which is how much work is required by the pump in kilojoule per hour, and what is the heat duty of the heat exchanger, also in kilojoule per hour. So basically, this is a simple way of presenting the information that I want to find from HYSYS. All right. So you might be asking, wait, I don't want this unit to be kilojoule per hour. I want it to be in kilowatt. I don't want this unit to be in kPa. I want this to be shown in bar. I don't want this to be kilogram mole. I want to be in mole. So is it possible to change all this? The answer is yes. So what do is I go to this, I go to the home tab. Below that, there's a units setting. Here you can click on this. There are some like preset unit settings. For example, currently I'm in SI units. I can go to UOSI. We should change this to bar. We should change the info to kilocalorie per hour. I can go to safety SI. We should go to bar G. I can go to SI bar G. I can go to European SI. I can go to American units even. I'm going to go to American units, which is called fuel here. So it goes to Fahrenheit, PSI, pound mole per hour, pound per hour, and so on. In this case, I'm just going to go back to my SI because I'm not used to looking at American units. And let's say I want to change a specific, a specific item in the table. I want to change it flow to kilowatt. I don't want kilojoule per hour. This unit is a bit weird, right? What I do is I click on unit sets. And then here, available unit sets, I can create a new one. Or I could edit the old one. So let's say I just call SI, then I'll just select SI. And I'll go down to like heat flow. I'm just going to this. Okay, it's for energy here. And you can see the unit conversions and such. Let's go to a custom one. So let's say user field 3A, field 3B. And let me just take SI and copy as a new user set. So I want everything to be in SI units. It's just I want to change this energy to kilowatt. So when I am taking my custom unit set, I can just choose here. Let's put it to kilowatt. And I'll just call this SI underscore kilowatt. And then I click on OK. So now you can see the heat flow is in kilowatt. The pump requirement is 6.9 kilowatt. The heat duty for heating is 962 kilowatt, 0.7 kilowatt. So basically, this is how we start out in the flow sheet. We define the streams, we put in some blocks, and we show the results. So this is the most basic of learning how to use HYSYS. So I see the time is around 10:28 a.m. So shall we have a break now, Winnie, or how?
All right, sure. Okay. So thank you very much, to Mr. Teo for the great info. Now we will take a break for 15 minutes before continuing to our next session. You may come back at 10:45 a.m. Thank you. Ladies and gentlemen, now I would like to invite Mr. Dior to continue the next part of our session. Please welcome.
All right, thank you, Eli, for introducing me again. So let's continue with the fun part today. Right, so let me just stop my camera so I can improve my bandwidth a little and reshare my screen. Okay, so before the break, right, we stopped at case study 2, item number A. So how much heat is required for the process? We have obtained the value of 962.7 kilowatt. All right. So that is the easy part of this problem. The second part of this problem is more complicated, and it's actually based on a real problem that I had in my workplace. So Pons is thinking whether to supply the water at 10 bar G. He thinks higher pressure equals lower density equals smaller pipe size. Is he right? So the situation here would be that, for example, this new pipeline to supply water to this refinery might have needed to come from somewhere far away, maybe 200 meters, maybe 500 meters, right? So when you're building such a long pipeline, the size of the pipe matters in the costing and the cost of the new pipeline installation. So Ponce's idea here is, why don't we install a pump at the start of the pipeline, pump it to 10 bar G, transfer it nearer to the boiler, then only pump it back to 20 bar G, and to see if that will actually lead to the smaller pipe size, which is due to the higher pressure and lower density. So let's see if this is actually the case or like he's wrong. I think you can guess the answer by now, but we just show it from the HYSYS. Just let HYSYS tell us the answer. Okay, so we are back in this flow sheet, which I'm just going to just show you guys that it's the same flow sheet from just now. And we're going down to utility water. And so this guy is going to is thinking of installing a new pump. Right, so this guy is thinking of like installing a new pump here to make it to pump the water to 10 bar G, only then transfer to P100, which then goes up to 20 bar G. So let's pretend that we have pump in front. We are going to look at the density, which is 1007, and then I will change this to 10 bar G. Sorry, it should be 10 bar G, so it should be below. Bar gauge. Okay, so we have 10 bar gauge. We look at the property again. The density has increased by a total of 1 kilogram per meter cube. So that means that there's actually not much difference in pumping water at 10 bar G or 20 bar G. You still have to buy the same pipe size. And if you know a bit of thermodynamics, you realize this in the first place because compressing a liquid doesn't change the density very much, and water is liquid under these conditions. Okay, so we have managed to find this. But what happens if, let's say, there are many other cases that you want to evaluate? So now we only have atmospheric pressure and 10 bar gauge, 2 conditions. So we can just change the property and have a look manually, right? That will be the way to go. And what happens if we have many conditions that we want to, maybe 10 different conditions? We cannot be changing one by one, right? Because that would be like very time consuming. So that, sorry, this is the flow sheet blocks, which we already covered. And that is what we are going to do next. To prove the case, Bonds asks the theory to simulate and check the volumetric flow of the required water at various pressures between 0 to 10 bar G so that he can evaluate the required flux sizes. So if I want to know a physical property at many different conditions, the easiest way to do this is by using the case study tool, which I'm going to show you how to do that. So a case study consists of manipulating an independent variable, then recording the response in a dependent variable. Okay, so let me just go back to the HYSYS here. I'm going to just reset this back to atmospheric pressure. And I'm going to run the case study tool, which is on the home toolbar. Case studies is right here above the analysis tab. Just click on it. Click on add. And I have case study 1, which now allows me to define the variables that I want to see. So the first thing to do is to select the independent variable. So I must click on find variables. So I'll choose what I want, which stream I want, which is utility water. Double click on that, and it shows all the properties that I can manipulate. So in this case, it will be pressure. So I just select this and click on done. So I only have one manipulated variable. Then the dependent variable here would be, again, click on find variables. Now click on utility water. Here we are going to look at the mass density. So you can see the density difference. And you might also want to just look at the volumetric flow rate. So it's something like liquid volume flow at standard condition. No, it's not this one. I think it should work in this case because it's liquid. So I'm just going to click on done. And then I'm going to move into case study setup, the second tab, which is where I decide how many steps I want. So what I need to do is in here for start, I will type in the start value. The ending value will be 10 bar G. So maybe 1103.325. And then I want to have like 10 steps. So now maybe it's 11. So the difference is 100. So the step size is 100. And then I can just click on and take this reset after run, or click on this. Then it will just decide whether it resets to the start after it runs. And then I just click on run. So the status shows success. We look at the result. So this is the density at the 11 different cases. This is a flow rate. And then I can also click on plot. So I can choose the variables on the plot. So I'm going to choose on pressure as the x-axis, and then the utility mass density and the y-axis. You can see that the pressure has changed very little. The density has changed very little. In fact, even the decimals don't show a difference until 7 bar G. I can also view a liquid volume flow. You can see the liquid volume is basically the same. It's so small it cannot be seen. Right? The difference is so small. So this is what we call a case study. And it allows us to vary a certain parameter and to look at how it affects another parameter. So I've shown you the case study result. So in this case, right, it will not make any sense to just get second pump. You should just buy one pump and that's it. So a little bit of notes about how to select the correct fluid package. The correct fluid package selection depends on what components you have, what is your temperature in the flow sheet, and what is your pressure in the flow sheet. So like there are many like flow charts or many guidelines on what to choose when. But this is one of them. So for example, we start from here. Classify all the components you possess, your gas, non-polar, associating, solvating, electrolyte. Is it all gas or non-polar? If yes, then you choose Peng Robinson, SRK. If it's electrolyte, you choose this. If it's not, then so on and so forth. So this is some guideline about what, how do you choose the required fluid package. And there are also some choices that are for specialized applications like gas dehydration. So maybe the best is sour water stripping, which is a refinery process. Maybe sour beer. Cryogenic gas processing, maybe is air separation, atmospheric crude distillation tower, ethylene tower, high hydrogen, and so on and so forth. So there are like some specialized fluid packages that are designed for these applications. So this is a case study without example that I showed just now. So like you can see that the mass density, the unit is very small, but this is actually like 1007 over here, and this is like 1008 over here. So the density has only changed by 1 if we increase the pressure by 10 bar. All right. So second tip I want to share is always cross-check with something you already know before you proceed with any simulation. Because if you can catch your mistakes early, they will be much less painful for you in the future. You want to catch the mistake as early as possible if there are any mistakes. You don't want to like catch a mistake at the end of the project when you want to submit to your lecturer or to your boss or something. Then you won't have the time to fix it. Right. So I'm just going to try one example with butane. I'm going to try one example with butane, and I'm going to compress butane from 10 bar to 20 bar. Sorry, I'm going to I'm going to compress butane from 10 bar to 20 bar using a pump. So let me show you this. All right. So I'll just start a new case study. I need to start a new case so I don't overwrite this old file. Okay, in this component, I'm just going to put butane. I think should put N butane. And then I will just put a second one, which is high butane. Okay, in the fluid package, I will select, since it's oil and gas again application, I'm going to select tank Robinson. And I will go into the simulation screen. I will put in one stream, which is just for one, a pump to 2. This butane, this stream will consist of let's say temperature of 50 degrees, pressure of 10 absolute bars, and composition will be 75% butane, 25% I-butane. And then you can click on equalize composition. Then it will normalize the composition to each one. Or you can click on normalize, then you will normalize to get total equal to 1. So in this case, right, just now I type 75 and 25. You click on normalize, and then you will make it 0.75 and 0.25, so that the total is 1. So this is a very helpful tool in case that for some reason your composition doesn't end up to 1, maybe because of some errors or some measuring issues or something. So, and I'm just going to make this 100 kilomole per hour. So now this stream is fully specified. Choose pump. Connect this pump to 1. And then connect the outlet. I need energy stream, so I'll just go out edit. Okay, so I'll define the outlet pressure as 2000 kPa. So you get pumping, you get this butane mixture being pumped from 10 bar to 20 bar. Temperature increased by about 1 degree. So power is 4 kilowatt, and nothing special, everything works, right? But what happens if, let's say, I change the inlet condition? Let's say it wasn't 50 degrees. Let's say it's 100 degrees. You get some issue. The issue given, look at the warning, vapor in inlet stream. So I'm wondering why is there vapor in the inlet stream, right? Let's go back to the phase diagram of butane, which I'm just going to show it here. You can see that if I were to have 10 bar and 100 degree, this will be in the gaseous phase, and you cannot pump the gas. You cannot pump the gas. You can only pump the liquid. And because the mixture is 75% butane, it's most probably also somewhere to be very near this point. And if I look closer to using an engineering toolbox link, which I'm shown in the chat, you can see that at normal conditions, about room temperature, at 10 bar, butane is a liquid. But above 79.5 degree, butane turns into a gas. So it now creates errors if I try to pump it. And this is sort of the common sense that we need to have a sense of before we when you're doing. So in case you get some error, you don't panic. Oh, wow, what happened? What happened? Oh, it turns out that we are trying to pump a gas and you can't. Another clue would be to look at the density. Usually a gas density is around 10 to 100 times smaller than the liquid. So for example, right, you look at this density is 500, goes down to 25. So there's a 20 times drop. So it looks like there's going to be a phase change in the substance. So if I go back to this stream, and we set the pressure to, and we set the temperature to 50 degrees. I look at the calculated density is around 500 kilogram per meter cube. I increase the temperature to 100. I go back to property. The density has dropped to around 22 from 537. So that is a clue that there is some phase change happening that we did not expect. All right, and that is why your pump is not showing an error. Because having vapor during the pump will cause something like what we call cavitation, which will damage the pump in real life. So that's why it's showing an error. Okay, and the next tip that I have is before we start moving to the heavy stuff. Yeah, before we start moving to the heavy stuff, it is important to have safe files because HYSYS is very prone to crash for no reason, especially when your flow sheet gets more and more complicated. So it is quite important to make sure that you save frequently. But you also reduce your pain by first having multiple save files and save over this milestone. For example, I have defined the stream, I save. I have set up the equipment, I save again in a different file name. Then I have gotten the result, I save again under a different file name. So this will ensure that when something happens, I can recover my work. I don't have to do everything from scratch. You can also save as two different file formats. The first is called HSC, which is HYSYS case. And the second is XML file format. The difference between these two main file formats is that the XML will not remember your result. It will not remember your result. So you have to run the simulation to get the results. Whereas the HSC will remain the old results. So in many cases, you want the old results to be saved. But in some cases, if your simulation cannot converge for some reason, you might want it to reset the results. So you can load this XML file, and then the results will start from 0, and then you recalculate again. And next is also to read from error messages and learn from them. Don't ignore the errors because they usually tell you what is happening. It's just that they don't tell you what you need to do. So you don't have to learn that either from the in-program help or from experience. So let's move on to the third case study we have for today, which is the reactions. So you can go back to this slide, right? We see that there are 4 main types of flow sheet blocks. We have heat transfer, we have pressure changes, we have reactors, and we have separators. So if I And we have covered the simple ones. I started with the simple ones, the pressure change, where you only need to give it the pressure change, which is the pump here. And you also have a heat transfer block where you need to give it the pressure difference. You also need to give the heat duty, right? So these two are like very simple blocks that anyone can program. The next two are going to be tough because they require a lot of inputs. And we go for the easier one, which is the reactors. So let's look at reactions. So in chemical engineering, certainly we need to have reactions. Otherwise, that's not chemical engineering. This is able to simulate very rigorous reactions, very rigorous reactions. But the issue is that the issue is just that you need to have the reaction data, which is quite difficult to get. And in many cases, the heat of reaction needs to be considered. So your substance, whatever that's having a reaction, might get hotter or might get colder, depending on whether the heat of reaction is negative or positive, or you could say that the reaction is exothermic or endothermic. Alright, so Dave has another friend today whose name is Tans. So if you are a bit perceptive, you realize that there's a team naming to Dave's colleagues. Right. So Dave's colleagues Duns today wishes to model a new hydrogen production unit. Because apparently this refinery has a hydrogen demand. There are some customers who buy hydrogen or something. But Duns is not sure which reactor type is the best for this application. So in this so-called hydrogen production unit in the refinery, the two most common reactions we have are steam methane reforming, or SMR. Where you take methane, you react with steam, produce hydrogen and carbon monoxide. This carbon monoxide then goes into what we call the water gas shift, or WGS reaction, where you react with more steam to produce hydrogen and CO2. So the final product should be only hydrogen and CO2. So we are very lucky today that these two examples are very simple examples that HYSYS have the kinetic data in its built-in library. However, I'm going to show you how to input the kinetic data ourselves, because in reality, you are getting kinetic data from a textbook, you are getting it from a journal article, you are getting it from a conference paper, maybe, or maybe in your own lab results. So in these cases, HYSYS will not have these kind of reactions and you will have to input them yourself. So I'll just show you by doing the first one manually. And for the second one, we will do it, this one we'll do it manually for the steam methane reforming. And second one, we'll just see how we can import the HYSYS reaction. All right. So these two reactions in the hydrogen process, I'll show you the air products hydrogen production unit, where your natural gas going in. You take out any sulfur you have in natural gas to prevent catalyst poisoning. It goes into the fire heater, and it goes into, so the gas goes into here, it gets heated, and then it goes into these tubes. And there's some catalyst in these tubes where the SMR process happens. So the SMR is a catalytic process. Then the gas goes out, a mixture of hydrogen and CO. It goes into a boiler to reduce the temperature to the suitable for the next reaction. And then it goes into the water gas shift reactor, where this is where the WGS reaction happens. And then it goes into some cooling and further purification before the hydrogen goes to the customer. So we are going to simulate this and this. So in real life, you will do it in different reactors, but in this case, we will just do it in a simple way, which is we just combine into a single unit. So there are three main types of reactor models in HYSYS. The first type is called equilibrium, which is calculated based on chemical equilibrium. So the equilibrium has to be defined by you, by the user. The second reactor is called the Gibbs reactor, which you don't have to define anything. You just tell HYSYS these are the components and these are the products. HYSYS will adjust the reactor itself to minimize the Gibbs free energy of the products. So it sounds easy, but later I'll show you why Gibbs reactor is not necessarily the best way. In many cases, it's very, very inaccurate. And the last method is to have a kinetic reactor, which will need us to input the kinetic model or the reactions ourselves. The two most common will be the continuous stir-type reactor for liquid or aqueous applications, and then the plug flow reactor for mostly gas reactions. So this is the one that we are going to use for the plug flow reactor. So I have gotten from a source the rate equation for the SMR process, which is quite complicated. All right. And these are the units. So we'll use this information only for reaction 1. For reaction 2, we'll just use the built-in reaction library. So don't make our own life more difficult than it needs to. All right. So I'll just go back to my HYSYS script. Let me see if I can show side by side the data. Okay, so I have shown. Let me see if I can show this here. And I'll just share my screen again. Okay, so I'll just create a new case. I'll close the old case. Okay, let me go on to the next slide. So components list. So again, we have to define the component. So I've shown you the components here, which are CO, H2O, CO2, H2, CH4, and N2. So I'll just put them all in. So we have carbon monoxide. We have hydrogen. We have water. We have carbon dioxide. You can search for a name or a symbol, both will work, unless there are multiple components with the same symbol. So say methane. One more is nitrogen. Okay. So again, for fluid package, we will choose King Robinson, which is quite common for SMR reactions. We go into simulation menu, start dropping in the feed. So I'll do these things faster because I think we are all more used to it by now. So I'll just call this SMR feed. And we will just type in the required details. Okay. So we have 350 degrees Celsius. We have pressure at 30 atmosphere absolute. I'll just purposely give you different units all the time, so that you get used to like changing units once in a while. Yeah. So in reality, you're mostly going either bar or PSI. So you won't have like ATM absolute as a, usually you won't have this kind of like units. So we have CO is, I'll just click on edit here. Everything will be in mole fraction, so CO will be 0.98. Water will be 0.307. Hydrogen will be 0.05. CO2 0.04. Methane would be 0.1. Nitrogen will be 0.15. So nitrogen is not involved in the reaction. It's just an inert gas that sometimes appears in certain streams inside a real refinery. So the total is 1. Okay, so that means that is correct. I press OK. And I'll just give it a flow rate of, let's say, 1000 kilomoles per hour. Okay, so we get everything done. Now we have a SMR feed. And then we will pop in the reactor unit. So for the reactor unit, just click on reactor in the water palette. The first is the continuous stir tank reactor, CSTR, plug flow reactor, equilibrium reactor, Gibbs reactor. So I'm just going to put in the plug flow reactor. Okay, so again, it's not specified, so let's go into the plug flow reactor and connect the required. Inlet VSMR feed. The outlet will be a different stream, but we can do that by just, if I want to create a new stream and I'm lazy to drop it in the, if I'm lazy to drop it in this like flow sheet, like I can just type in the name here, SMR dash product, for example, and you create a new stream on the flow sheet once I press enter. So this is like the easy way to do it. And then when I click on reactions, this is where I define the reactions. You find that there's a reaction set that I need to fill in. So this is actually where I put in the reaction information that I require. This is where I put in. So I can't do anything now. I need to go back to the properties window and configure the reaction sets. All right, so let me just go back to properties again. Like on the left side of the screen, there's a folder called reactions. So I can click on add. Then you create a new reaction set called set 1. And then I can now press add reaction. So here, it asks me to choose between 5 different types of reactions. So simple rate is can be ignored basically. Most of the reactions we have will be equilibrium, heterogeneous, catalytic, or kinetic. So the SMR process is a catalytic reaction. So I'm just going to put in heterogeneous catalytic. Heterogeneous meaning that the catalyst is not the same phase as the reactant. So we have a gas as a reactant, solid as a catalyst. So this will be the choice that we want. That reaction. I just close. And then I double click on the reaction to define it. So this is the most difficult part of trying to define the reaction. Okay, so what do we do? First, we need to define the reaction stoichiometry. So the reaction is CH4 plus H2O to become 3H2O plus CO. So we put in CH4, H2O, H2, and CO. And for each component involved in the reaction, we have to define the coefficient of the reaction. The reactant will have negative, so -1. Product will be positive, so +3, +1. So this is how we define the stoichiometric coefficient. And then I think here should be all right. Basis molar concentration, no. Because this is a gas reaction, we are going to use partial pressure. And the reaction phase will be in vapor phase. Or you can also put overall, since there's only one phase. Putting overall is the same as putting as vapor phase. The basis unit will be kilopascal, okay, fine. No, not Pascal, because our base unit is ATM. Weight unit is kmol per meter cube per second. Okay, then. Okay, let's say our weight unit. So in this case, the unit is actually mole per kilogram per second per ATM. So our pressure unit has been ATM. Otherwise, it will not make any sense. All right. So this is the easy part. Now we move on to the reaction rate. This is very, very difficult to fill in. And there's actually a help button here. You can click on it. So it shows the formula that we must match in order to successfully fill into this reaction rate. Let's compare what they have and what we have. Let's compare what they have and what we have. All right. So I'll just set the screen to both sides. And okay, now you can see both sides easily. The rate equation that we must match is numerator over the denominator. That's where we have a numerator, which I will put in red color, over denominator, which I will put in blue color. Okay, it looks like good. At least we have the starting, at least our equation is in the correct form. Something over something. Okay, that makes it easier. And the numerator has to be a constant multiplied by a function of the basis. This is the partial pressure that we choose. Minus something. In our numerator, we don't have the minus part. We only have a positive part. Okay, that means that we could, if we could eliminate this part on the back, it will be easy. So we just focus on the front. So the K, looking at the equation, is equal to A multiplied by exponent negative E over RT multiply T times beta. So let's match the K that we have. So we have this part, which is the A. I'll just highlight this part. We have exponent part, which matches this part of the exponent. There's a T here, but we don't have. And then there's a partial pressure here, because P is the partial pressure, Ym is the mole fraction. When you multiply the total pressure by the mole fraction, you get the partial pressure. Then you get the denominator. So it looks like we could fit into the weight equation, but we need to do some calculations. Okay, let's see how we fill in up. So the forward reaction, A is rho weight multiplied by Km. But the unit must be in kilomole, not mole. So what we can do is, we can manually multiply these two numbers. We can manually multiply these two numbers. So, and then we divide by 1,000. So if my calculation is correct, this number should be equal to 620. So what I did is I multiply rho weight times Km, divide by 1,000 to change the unit from mole to pitomole. The units are very, very important in the weight. If you put in the wrong unit, your weight will be 1,000 times faster or 1,000 times slower. Both of which will lead to some crazy, very crazy results. Right? And E here, looking at the equation, E is simply this number. This is just E, negative EA1. So I just put in this number, copy exactly, 1.849 exponent 8. That's it. And we have a beta, but we don't have this t term, so just set beta to 0. Easy peasy. Then we have settled the first part. We don't have the reverse reaction part, so just ignore everything. So that's the numerator part done. Now we go to the denominator. The denominator here is 1 plus KH plus partial pressure of H. So H is hydrogen. Sorry, I missed one thing. This is PYM, right? The denominator only has one term, which is the partial pressure of methane, and this is raised to the power 1. So in the component, forward order, I should put 1 as methane, delete the water. And reverse order, I should delete everything because it doesn't exist. So that will ensure that the HYSYS doesn't go and calculate wrongly, put this term into the equation. So forward order is 1. Okay, so now our numerator is correct. Look at the denominator. The denominator is 1 plus KH partial pressure of Y. So the denominator here is 1 plus K1 multiplied by F1 of the basis. So F1 of the basis is basically this partial pressure. So we just put methane as 1. The rest will be nothing. The A would be K1 will be A1 exponent this, right? So the exponent will be 0. And then the K1 will just be this KH. So in this case, the value would be 4.053. Okay, so painstakingly, we have managed to fill in everything that we need to. Sorry, this is not methane, this is hydrogen. Okay, so we have finally managed to fill everything for the first reaction. And this is considered quite a simple reaction. If you have like reverse reactions and equilibrium and stuff, it's even to be more complicated than this. So we are quite lucky that we only need to fill in for the first reaction. For second reaction, I'm just going to import whatever that I have, whatever that this HYSYS has. So this is the first reaction done. The second reaction is the water gas stream reaction. So I'm going to click again, add reaction. In this case, it's going to be in equilibrium. Close. Reaction 2. There's a library tab here. Click on the library tab. You can see that this reaction is actually the first in the list. Just double click. It's done. Completely configured. But before we go into the flow sheet, we have to add to the fluid package. Which means that just to tell HYSYS to use this fluid package to calculate this equilibrium. And then we can now go back into our simulation and then attach that to the reactor. So we are back here, double click on this. In reactions, put reaction set as 1. And then we have more info that we need to fill in, which is the PFR setup. Length will be 10 meters, diameter will be 2.1 meters. So we will fill them in rating. So I'll just print the length as 10 meters and diameter is 2.21 meters. And then finally, delta P I will just put at 0 because we are ignoring it for now. And I press enter, I get my results. So let's go on worksheet and look at the results, look at the compositions. So you can see that methane plus water forms CO and hydrogen. So the hydrogen increase and methane and water goes down. And then the second water gas stream reaction reduces the CO to produce more hydrogen and CO2. So this seems logical based on what we have, based on the theory of the reaction. This looks like it should happen, right? This looks like what's going to happen. So now let's try with the two other reactor types, which is the equilibrium reactor and the Gibbs reactor. So we go for the easy one, the Gibbs reactor. Again, click on it. Okay, this is a Gibbs reactor. So it's a Gibbs symbol here, in case you didn't see it. And then I'm going to do the same thing and attach the streams, feed, product. The funny thing about Gibbs reactor is it actually needs a second product, but I'm just going to not put it now. And I'm just call this Gibbs feed. So this stream will be exactly the same as a muffin. So I just want to type the same thing twice. So I can click on define from stream. Click on this. Available stream. That's the muffin. You can see the stream conditions here. That's okay. Then you copy everything into the new stream. So that will save you some time. Just going to define the Gibbs reactor. Inlet will be Gibbs feed. Vapor outlet will be SMR, 2. And then we need a liquid outlet. So I'm just going to call this like a new stream, Gibbs liquid, I mean a new name. You will format for it myself. Now I'll just change this name to Gibbs product. And you can see that I did not need to fill in anything else in the Gibbs reactor. The reactor has just solved itself for some reason, right? So let's look at the reactor. What happened to it? Reactions, Gibbs reaction only. Rating, no rating because I didn't specify anything. Then look at the worksheet. So the main difference here is that first, actually there's no liquid product because the liquid product, the flow is actually 0. But when you look at the vapor product, which is the gas product, the temperature is almost double to around 661 degrees. Yeah, what just happened, right? Then we look at the composition of the products. You can see that the composition, right, the hydrogen and the CO actually drop. and the water and the methane should increase. This means, right, the reaction has actually proceeded in the backwards direction. That means that according to this Gibbs reactor, this reaction is actually happening backwards. So it's actually taking this H2SO to reform the methane and water. Same also with this. This reaction actually proceeded forward because it produced more carbon dioxide. So is this actually logical? The answer is no. And the reason why the answer is no is that in real life, in a real reaction, we have catalysts in the reactor, which will catalyze the forward reaction. And that is why we can get the product in real life. But if we are just relying on the Gibbs energy minimization, the theoretical formation would be that the reaction will proceed backwards. So logically, we won't want the reaction to proceed backwards, right? Because you're not producing a product. You're wasting your product to produce more reactor. No, it doesn't make sense. So this is why the Gibbs reactor must be used with caution to ensure that what you're putting in is actually the correct assumption that the Gibbs reaction works. So in this case, it doesn't. The reason being that the catalyst actually helps to catalyze the forward reaction, and the Gibbs reactor does not consider any catalyst. That's why without the catalyst, the reaction will proceed backwards. So this is the magic of the Gibbs reactor. So it's very good when you're trying to like just get a feel of the reaction, but it's not good when you actually try to model the reaction, even though you don't have to input anything. All right. So the third vector I'm going to try is the equilibrium vector. So I'll just put that in here. And again, I can just create a new feed, or I can just take this feed, Control C on my keyboard, Control V. That will also do the same thing. So I'll just open this up. Heat sheet number 2, vapor outlet, I just call it equilibrium product. Liquid outlet, I'll just call it equilibrium liquid, which also doesn't exist, but I will have to give it this stream just to fulfill the requirements. And then I just rename this as EQ feed. Okay, so for equilibrium reactor, it is not under-specified. That means I need to tell it what reactions that it needs to consider. So when I go to reactions, I look at this reaction set and choose the set that I just defined. It doesn't work because the equilibrium reactor requires only equilibrium reactions. So it says the reaction set is not the correct type. So we need to go back to the properties window. Again, I will go back to the reaction folder. I create a new reaction set. I will create a new equilibrium reaction because the equilibrium reactor only accepts equilibrium reactions. Add reaction. Add one more reaction. So for the first reaction, I'll just upload this for library, the SMR reaction. For the second reaction, I'll just upload again the water gas stream reaction. So you don't have to do the typing again. I just put this in. So it's fully specified and add to fill package. Okay, everything's done. Go back to simulation window. Go back to the equilibrium reactor. Put this in, and automatically HYSYS will calculate everything for us. So let's go back to the worksheet again. Again, the temperature has increased to 659. Composition, again, CO has dropped, hydrogen has dropped, although slightly less than the Gibbs factor. Methane has also increased, which means that the first reaction has again proceeded backwards. So again, this also shows the equilibrium data is not correct because it is not considering the effect of the catalyst, it's just considering the effect of the chemical equilibrium. But the equilibrium data is usually more accurate than the Gibbs reactor. So if you have a chemical equilibrium data or equilibrium reaction, you can put it into the reaction set and then you can use the equilibrium vector to come with the correct, to come with a more accurate result. So these are the three main reactor types. So this is just very simple demonstration of how you set up each reactor. And the fourth reactor type, which is the CSTR, I'm not sure because I cannot use the CSTR in the gas phase reaction. So I need the liquid phase reaction to do that. Right. So we are now completed this. Let's go back to slides. And we have filled in everything. So the fourth tip for today is I've accidentally closed or hidden or deleted something. How do I get it back? Sometimes maybe I just accidentally close this model palette. And then I can't find, oh no, I don't know where the model palette is, right? So the shortcut to call the model palette is F4. The model palette will show up. Or the normal way to do it would be to go to your flow sheet, to go to the flow sheet tab here. Click on palette, models, and screens. Then you will show up again. What happens if I accidentally close the whole flow sheet? Click on view, click on flow sheet. So that's what happens. And another few other tips is that flow sheet find object is quite useful. So let's say you go and flow sheet here, you can click on find object or F3. It will show everything that exists on your flow sheet. So in case that you have accidentally moved this reactor out of the screen, you can still find it in this way. And also on the left-hand bar, sometimes you have to open up the folders to see what's inside. And for example, unit operations will show all the equipment on the flow sheet. So again, if you can't find it, just click on it. And then it shows you the menu for this equipment. If all else fails, press F1 for help. So if really you cannot find anything, you just press F1. And the in software help will show up. And the good thing about this help is that it is specific to what you just opened. For example, I just open the PFR, I press F1, it will actually show what tab that I'm opening. So if I go to rating, I press F1, it goes to the PFR rating page. So the help menu in HYSYS is very specific and it will know what you are trying to see. For example, you go to reactions, press F1, it goes to the reaction info page on the PFR. So that's a very helpful tip to know in case you get lost. Just press F1 and make sure you just open whatever that you're trying to look at. F1 shows the detail page for the equilibrium reactor. Very, very handy feature. So keep this in mind and then it will make your life easier. So let's go back to this and all right. So before I move on, are there any questions? Maybe I can answer them before we move forward. Winnie, are there any questions in the chat or anyone wants to ask any questions? Because I can't see the chat or the participant list.
All right, Ken. So far has one question from Lo Jiachen. He says, sir, I would like to ask, does HYSYS have positive displacement bound? If no, what should we change in the parameters in HYSYS?
Okay, thanks. Interesting question, which I've never received this question before, but yeah, we can answer that. So HYSYS does not have positive displacement pumps. Actually, HYSYS does not even differentiate what kind of pumps present in HYSYS does not even differentiate between what kinds of pumps exist in HYSYS. So if you look at pump icon here, it is just a pump. There's no difference. And the difference only comes in when you are trying to input the pump curve. So if you have the pump curve for the specific pump, you can actually feed into the equation. And then you type in the coefficient here, or you could go to the rating screen and you feed in the pump curve by clicking on the curve and then click on add curve. And then you can fill in some points that you get from the pump curve. And then you can regenerate the pump curve that you have from your pump datasheet. So the answer to the question is no. HYSYS does not differentiate between any kind of pump actually. Centrifugal, positive displacement, screw, it doesn't differentiate. But you can at least capture some of the differences in the pump type by using the pump curve if you have them. Yeah, so that will answer the question. There's simply no distinction.
All right, thank you. So for the next question from Nala Kukala, can you discuss how to determine hydrate formation using Aspen Plus?
Thanks, Kala, but I think you joined the wrong class because this is a HYSYS class, not Aspen Plus. So I guess you can do that Aspen Plus, but it's not for today.
All right, thank you. So for the next question from Abid Salam Faraki, kindly discuss about reducing reboiler duty of strapping column using Aspen HYSYS.
Thanks. That separation is something that we are going to cover in the next case study, but you're talking about reboiler duty in a sweeping column, I presume. So the reboiler duty depends on two things. The first will be the vapor flow in the column, and the second would be the boil-up ratio in the column, which is in the ideal situation is the same as the reflux ratio. So you can do that by reducing the reflux ratio or boil-up ratio of the column. If you're using the shortcut method, then reflux and boil-up is the same. So you can reduce that, or you can reduce the vapor flow from the reboiler to the column. The issue with doing that is you sacrifice the bottom component purity, because if you have higher reflux ratio at the higher boil-up ratio at the reboiler, you would have a higher bottom component purity. So if you get a very high reboiler duty, then you might need to think of reducing the boil-up ratio and the vapor flow to see whether you can still achieve what you want with a lower, with these lower parameters. If not, then it means sacrificing the bottom purity. Just drop the purity and you see your reboiler duty drop a lot. So that would be my answer to your question. I hope that helps.
All right, thank you. So far we don't have any question. All right, so if anyone still have any question, can still post it in chat box or can directly open your mic. And we will wait for 1 minute more. Okay, have next session.
Okay, thanks, Vinny. So we'll go to our last but longest case study for today, which is the separation part of the, which is doing like modeling separation processes in HYSYS. So there will be no chemical engineering without separation, because the fact is that most reactions in the world are not complete reactions, they happen partially. So like the SMR reaction I showed just now, the water gas reaction, it happened partially. And when you have a reaction which happens partially, we need to be able to separate the unreacted reactants and the product. Otherwise, how do we sell the product? We can't just take the whole thing and sell to your customer, right? The customer is wondering why you have like so many other things that they did not want in the product you're selling them. So separation is key. And obviously, HYSYS supports separation processes. The common ones are distillation, stripping, adsorption, liquid extraction. And these are usually modeled by columns. These are usually modeled via columns. We also have adsorption, which is the physical separation process, which you can't really do very well in HYSYS because they don't. Adsorption is normally a batch process where you have multiple vessels, and then you run one vessel in adsorption, and then the second vessel is on regeneration and so on. So that's not something you can do easily in HYSYS because HYSYS is only a steady state simulator. You can also do membrane separation, but you have to program the membrane details yourself. And I think membrane separation is starting to gain traction as more and more people in industry do like membranes. So let's go to case study 4. So Dave's yet another colleague. Dave has a lot of colleagues today. His name is Klutz, and he's required to design a new N-octane production unit. So octane is a component in petrol, and let's assume that because people are driving more nowadays after COVID, after lockdown and lifted, and there's more demand for petrol. So this company is thinking of producing more petrol. So this will be something like an expansion project. So this unit will produce N-octane from ethylene and I-butane as the following reaction. Two molecules of ethylene plus I-butane to form N-octane with some nitrogen and N-butane as inert in the feed, which for some reason or other cannot be removed before entering this reactor. And this reaction is also a reversible reaction. It's quite common that most reactions are reversible in the world. The unit shall be modeled as a combination reaction and separation unit as follows. I'm going to give a conversion vector, which is a very simple vector type. And then I'm just going to use a shortcut distillation column. If you have more time, you can go into like the more detailed kind of distillation column. Okay, so let's start out with the conversion vector setup. So let me just keep this, make it smaller, and I just open my new case. Just ignore this old case for now. Well, I think I should start closing up the old cases. Okay, so let me just add in the components that we have. So we have ethylene, N-butane, I-butane, and octane. It's not this. Ethylene. Value. Let's start another name. T. Why you give? It's T2H4. No, still not you. No component match. Cannot be. Minus. We just add other components. It's annoying. Oh, I mean, just delete. Sometimes annoying HYSYS is that it just hangs for no reason and then you just don't show the component that you want. Let's see. Ethylene is here. Wait, where do you go? Okay, finally I got you. Italy. Then we have N-butane. We have I-butane, isobutane. We have N-octane. We have nitrogen as the inert product. And that should be it. 5 components. The package, I'll just go for Pangomycin again. I can go for SRK for this, but yeah, there's not much difference in that. Then go to simulation mode, start dropping in the stream. I'll just call this, let me see what name I used previously. Let's feed then. Let's call it feed. And the conditions that we need are 93 degrees Celsius and 20 psia. So that will be 93 degrees Celsius, 20 psia. And let's give it, in this example, I define it as kilomole per hour flow rate. So I don't have to give the total flow anymore. I just directly go into the kilomole per hour flow rates. Just put this in here and put this in here. Sorry, this one should be. Let me just check this screen here. And okay, so the ethylene will be 20 kilomole per hour. So this one I set to mole flow. Unit is kilomole per hour. Okay, 20. And butane will be 0.5. I butane will be 10. and octane will be 0, nitrogen will be 0.1. So 30.6 should be the same number here. Okay. Where did my model palette go? Okay, it's on the right side of the screen. Okay, draw a conversion vector, which is here. The conversion vector basically just takes an equation and it just specifies the conversion without actually calculating the equilibrium or the rates. So it's only good if you are guaranteed that you know what the conversion is. So with outlet, I'll just call it a product V for vapor, product L for liquid. Then go into reactions. Again, we need a reaction set. So let's go back to properties, do a new reaction set for this document. That reaction, this will be just a conversion reaction where nicely should not calculate any kind of kinetics. So the reaction is just 2 C2H4, so ethylene, the first one, -2. C4H10 is N-butane, -1, product, N-octane. So that's one. So balance is no error. So base component here will be, let's put, can't remember which one's the limiting method. Conversion will be put at a number, let's put it as 98%. So C1 and C2 are temperature dependent. So in this case, we are just fixing the conversion at 98%. So I not really care about the temperature. So just add to fluid package. Go to simulation. Now I can put in here. And the reaction is completely satisfied because I've already defined the required reactions. And you can go back and have a look here and go through. So if you calculate the composition, this will be a 98% conversion of ethylene. And butane is completely used up. So we have like product. Oh, I think I made a mistake. It should be N-butane should be limiting. Ethylene is the excess reactant. Okay, this one should be the correct one. And yeah, N-butane is a limiting reactant. Ethylene excess reactant. So we still have a lot of ethylene in the product. Okay, so we have a conversion reactor. Now we want to separate out. Again, product L has no function. It's just there because we need to define the reactor with the liquid product, even though there's no liquid product, as we can see, flow rate of 0. The next step will be to set up the separation unit, which is, in this case, I'm using a shortcut method. If you have learned something about the separation processes in your course, that would be the what you call the Wien-Underwood-Gilliland method or WUG method. So where I find that is, we go down to separator. And then here we have a shortcut column. So this is what I want. So again, just going to open that. So in a separator unit, you have a lot of things that interfere in. So in this case, we have inlet. So inlet will be product vapor. The top product phase will be vapor, everything will be vapor. Overhead vapor will be a new stream that I will call, let's say just call it distillate. Bottoms, I'll just call it bottoms because it's in it. Condenser duty, I'll give it a stream called Q101. With boiler duty, Q102. Okay, that will be enough to fill in this page. So the parameters, we have to fill in the light key and heavy key fraction. So light key is the main light component that comes out the top. Heavy key is the bottom. So we want the lightest component to be Italian. So Italian will be on the top. But I want to limit the Italian at the bottom to 0.0015 mole fraction. Heavy key will be the product at the bottom. I want to limit the bottom product. The amount of heavy key will be the N octane, the heaviest molecule. And then for the molecule, the highest boiling point. And now we limit that to 28%. Condenser pressure will be 15 psi. The boiler pressure will be 35 psi. External reflux ratio, I can just put 1. Too much population. Oh, yeah, it should be 0.028. So still not enough. All right, let me check again what I put there. Oh, thanks. Thank you. That should be correct. If the minimum version is too high for vision. Okay, so we just leave it for now. And then we slowly move up later on. So we get so it will give us the most important thing in shortcut column is it gives you this page. The minimum number of trays, actual number of trays, optimal feed stage, condenser temperature, boiler temperature, and vapor flows and so on. Not really sure why it told me that I can't accept this, which is quite weird. So it didn't give me the same error. That's just a weird thing of I see sometimes. I just going to give it this number for now. And you can see that the minimum number of trays and so on changes. Okay, so let's move on and see what do we need. So this is a separation process. So we have slightly messy here. We just move this around and buttons. So in this case, right, we might want to do something like optimization where you want to reduce the heat input. So we need one more heat input here, which is for the reaction. This reaction that is exothermic. So let me just put this into the design energy term Q100. When you put in the energy term, the reactor becomes not specified because it doesn't know how much energy is required. So I'll just set this to an isothermal reactor. That means that the product will be 93. Then that should be it. Let me see if I can change it now. Still black. That's weird. Well, let me try to reopen this case and we'll just see if it opens again. Okay, this is weird because now it accepts my 0.28. So I just assume that this is a bug in the latest HYSYS version. So see, yeah, it's accepting my 0.28. But perhaps it's just a bug. I'm not using the latest version. So again, the good thing usually we'll want to do is have the stream table. Again, we can do that by right clicking and then add workbook table. So in this case, we actually have 3 heat streams. So I'll just add in the energy streams here. So that we can see there's the heat flow difference, and then I'll just change the units to the unit that I just did just now. So Q100 is the heat removed from the reactor, negative meaning heat removed. Q101 condenser heat removed 16.6 kilowatt, and Q102 heat input to reboiler 13.91 kilowatt. So again, I can also add a table for the composition just to confirm that I've achieved my requirements. So you can see that for the distillation column P100, I'll just rename these two as distillate and product instead of 1 and 2. And so the bottom has a component mole fraction of Italian of 0.0015, which is what I inputted, in the input, and the top component distillate cavity is around 0.28. 0.2796 is around 0.28 because of the calculation tolerance, which you can change, but I'm not going to change it for this demonstration. So that's how you get like reaction and separation combo, which is quite normal if you're doing a plant design. You certainly have a reaction and a separation combo. It won't be like just pumps and heat exchangers and like. All right, so I'm just going to save this, and the next one will be our last case study for the last half an hour, and it will be quite complicated. So maybe I'll just stop here and see if you have any questions before I move on to the last case study. And I'll just leave it on the screen so that you can see if you have some trouble getting any of the results. So I think I'll pass to you then, Billy. Do you have any questions on the chat?
All right, sure. Now we have 2 questions. So for the first one, for a bit as well, does reboiler duty increase as the concentration of carbon dioxide increases in the sour gas?
Hi, Abid. I cannot answer this question because I have no idea what you're trying to do. Basically, you are doing something in sour gas and there's CO2 in it, but what exactly are you trying to do? So there are many factors that can affect what the reboiler duty is. What they're trying to separate, what is the product, what is the reactant, how do you set up, what's the flux ratio, and so on. So I can't answer this question without more information. Okay. So you probably need to give me some more information. Or you can try that out by using a design spec or case study. You can actually try it out yourself as well. You try to change the concentration of CO2 in your inlet, I presume. Then you see what the reboiler duty is. That's what I can tell you.
All right, thank you. So for the next question from Lo Jiachun, can we put reactor jacket in HYSYS?
Can we put reactor jacket in HYSYS? The answer is yes, but it does not design the jacket for you. Let's put it this way. So you can see that for this conversion reactor, right, there is a heat stream here. This will be your jacket. This will be your jacket. So you can see how much heat you need to design the jacket for. But it does not really design, there's no jacket design. So you have to do, if you are trying to come up with some calculations for the reactor heating jacket or cooling jacket, you have to do that externally out of HYSYS. So that will be my answer to that. That means that you can have a basic understanding of how much heat you need to remove, but there's no design for a reactor jacket in HYSYS.
All right, thank you. So for the next question from Habib, How applicable is aspenhysys in the analysis of a simple gas turbine cycle in refinery?
Simple
Gas turbine cycle.
cycle. All right, thanks. Usually we call that simple cycle gas turbine, but I presume that's the same thing. SGG. You can do that in HYSYS. You can do that. You need a closed loop Brayton cycle, and maybe the flue gas side, you want to model that, you can do that. I would say yes, you can do that. It's just that usually gas turbines, they will use like very specialized. If you really want very detailed design for gas turbine design, they will have very specialized gas turbine software from GE or Siemens or what. The simple answer to your question is yes, you can.
All right, thank you. So there is no question anymore. So I think can proceed to the next session. But if you have any more questions from the participants, so you can post it in the chat box.
Right, thank you, Winnie. So I'm going to proceed with our last example for today, which is the most difficult and the most headache inducing usually. All right. So, oops, sorry, I'll jump the first slide. Okay, so just now we were here, all right? So this is a flow sheet that I've just simulated in HYSYS. So you have commercial reactor and then you have separator. So these are the results, which is similar to what I just showed on screen. And the last case study for the will be for recycle streams. So let's go back and look at our results again. All right, so now we have a stream table, it's easier to see. Distillate. Let's look at the distillate line. Okay, in this case, right, N-butane is a limiting reagent. So the feed has this amount, product has this amount. Ethylene is not limiting. But you can see that in the distillate, right, we have a lot of ethylene. And this ethylene, if I just take it out to flare or something, it's just a waste of my money, right? Because it costs money to make products. So in this case, Dave is looking at the simulation results given by Platts. So you're wondering whether there's a lot of unreacted reactor in distillate that Platts is throwing away unnecessarily. Is it possible to put this reactor back into our reactor? And that can actually produce more like N-octane from the remaining unreacted N-butane as well. N-butane as well. So recycle streams are a major component of any chemical process. The recycle block is used, which follows a tear stream concept. So HYSYS has a recycle block. The recycle block does not exist in other process simulators like Aspen Bus, but it does exist in HYSYS. So I'm just going to save one copy of this file because recycle streams have a very high tendency of crashing on HYSYS. And I just want to crash in the middle of a demonstration. So the recycle block is here. Look at the manipulator tab here. There's a recycling symbol. This is the recycle block. And that is when you have a stream. For example, I want to recycle this distillate to the feed. I will need to connect it to this. If I just connect it this way, it will never convert to a solution. Right? So let me just see this. We will set up a recycle stream which recycles 80% of the distillate. 20% of the distillate will be purged. So I want to ask you guys, why do you think we should purge 20% of the distillate? Why I cannot recycle 100%? I can save more money, right, if I recycle 100%. So why do I need to purge a certain percentage of the distillate? Let me know in the comments what are your ideas. Right, 20% in this case is just an example, but it can be any percent, it can be 1%, 10%, 5%. But the important is that we just need to have this purge line. So let me know why do we need to purge that. Well, I move on to the how to specify this. So we are going to specify, this is how it's going to look like in the end. But this is how I will Let me just keep this, and let me just do the side-by-side thing again. Okay, so the recycle stream specification, I will first need to maintain a purge of 20% purge. And so let me just start doing the purge. Yeah. So first we need a T. A T is like an opposite of mixer. So I just go to all, and this second item is a T. Just put one T here. And then I'll just rotate it facing upwards so that it looks better. And you do that by pressing 3 on your keyboard. So button 3 actually like does the rotation. And I just double click on this. So this is the page specification page for the T. We have this select product. Outlet, I will just define 2 outlets. One will be called cycle. The second one I will call it purge. Okay. And then in parameters, we define the flow ratios of the separation between the two. So I would say recycle will be 0.8, and then purge will be automatically calculated as 0.2. Okay, that's good. So we have the 2 lines. So I want purge to be on the right side. No. So I'll just rotate this line so that they are looking towards the right direction. So recycle will go back. Purge will go to the right. Okay, now that's the first step done. I have successfully set up the purge. And now we need to think of how to put this recycle back into the feed. Okay, let's have a look at the recycle stream. Okay. Temperature 85, pressure is 15 psi. Flow mass flow is 67 kg power, which is actually very small, but never mind. Can we put this back into the reactor? Let's look at the reactor. The reactor is at 93 degrees Celsius. The reactor is at 20 psi. Can we say logically I cannot just connect this to this? Otherwise, the feed will backflow into the recycle because of the higher pressure difference. So the recycle will never enter the reactor because the reactor has higher pressure than the recycle stream. So the first thing I will need to do will be to recompress the recycle stream into the reactor pressure. Otherwise, it will never go in real life. I mean, you could technically do that in HYSYS, but it would just accept it as a result, but the result is not realistic. So I join the compressor here. I will use the 3 button to rotate it facing the left, and I will specify that inlet as recycle, energy as Q103, I believe. Outlet will be recycle comp. I just call it like maybe cycle compress. Parameters, not really much to set because I'm going to set using the outlet pressure. So in this case, I will define the outlet pressure as, in minimum, I'll need 20 psia, right? But because I'm going to do something later, I'm just going to give it some more. Maybe I just give it 22 psia as outlet pressure. So it will calculate the rest, and then the compressor will be completely specified. So let me just check this here so everyone can see it well. And change the recycle comp direction to the left so that it's actually going towards the correct direction. Move the recycle compressor label to the top. Then this will be the work done required by the compressor. And then I'm going to save it. Okay, the next thing that we need to tackle here is that the temperature is not the same. The reason being that when you compress a gas, the temperature goes up. Adiabatic compression heats gas. So if you keep recycling, the temperature of the reactor will keep going up as the gas gets hotter and hotter every time we recycle. So we need something to reduce the temperature. I will just do that using a cooler pot. So again, facing the left, inlet will be recycle comp, energy will be recycle cool maybe, and just call it Q104 then. Outlet will be recycle cool. Okay, so I just put this here, and I'll just drag this down so it looks more neater. Move size table, let's move it here. Okay, so it looks good now. This one will facing left side. And the outlet stream, I will define it as having the same temperature as in the 93 degrees. And then one last thing I need to do is the delta P, which I will just set to 2 psi. So if done correctly, the recycle cooler's outlet should have exactly 93 degree, exactly 20 psi. So looks like we have managed to do everything. And now it's time to put in the recycle block. Okay, so before I do that, is there any questions up to now before I proceed?
So far, no.
No questions. Okay, so going back to the previous question, why do we need this purge in the stream? So let me see if there are any answers, suggested answers, right? Okay. So the inlet feed enter, no, actually it's not because of inlet feed enter, because as long as the pressure is higher, then you can enter. So the reason to have this purge, right, is to ensure there is no accumulation of reactant product or inert, but usually inert. If you look at this distillate, look at composition. There are two types of inert here. I-butane is an inert. Nitrogen is an inert. So if we don't purge and we recycle 100%, the feed will have more inert. Then the next round, the inert will go out distillate, and then some inert from the feed will also enter the distillate. So you get more inert in the distillate, recycle again, even more inert, recycle again, even more inert. So the simulation will never converge because the system is not stable. It will keep increasing the inert. There will be more inert in the stream until maybe it gets stuck somewhere or it causes some other problems. And then we'll have they cannot converge the simulation because every time we recycle, the number will keep increasing and it will not converge. So that is why we need to maintain a certain number of purge. And what is the percentage of purge you need? That will have to be determined by some trial and error. But usually you can do that by calculating how much inert is here and how much inert needs to go out, so that the amount inert going out in the purge is equal to the amount inert coming in the feed. That's how you get the percentage. 20% probably a bit more, a bit too much, but it's just a number that's set in there. So I will now proceed in putting in the recycle block, which might take some time to converge. Okay, so let's see how we do that. First, we go to manipulator block. Look at recycle. Drop it here. So this is a recycle block, and I'll just open it. Put in recycle cool, so that we are just rotate it so that it looks better. Okay, so this is a recycle block, and the recycle block is the outlet, which I will be calling the recycle feed. Okay, so now we have everything we need. And can we just connect that into the feed? The answer is yes, but I won't recommend that because it's difficult to converge. So what I usually do is I will first disconnect the feed. So how do I do that? Click on feed, then flowsheet modify, click on break connection, hover onto this blue line, and then your cursor turn into a tick symbol, then press it. So the feed connection is now gone. Then I will insert a mixer before the feed. Yes, I will just insert this. Fit the back and put this mixer in front. So the inlet will be the fuel feed and the recycle feed, and I'll create a new outlet called a feed to reactor, reactor feed. Okay, so it's done here. And this reactor will need this as an inlet feed. So I'll just put this in as a reactor feed. Okay, so now the system is Let me just align this nicely. Hanging a bit laggy nowadays. So what is down here? Move the recycle block up. Okay, so now this is our complete recycle loop. And we can now export again the workbook tables, the material streams, the compositions, the energy streams. And from here, you have a complete but simple plan that contains all the necessary basic models, the pressure changes, the heat exchangers, the reactors, separators, and most importantly, the recycle loop. So this is basically you can say this is a complete simulation. And as similar to what I stated at the start, right? You can actually go in and start adding more detail to the reactor. For example, this might need two reactors in series. This compressor might need some intercooler between them. Then when you have multi-stage compressor, this might need multiple distillation column and so on. So we can now go in and do that. But that is all today. So today will be a simple demonstration of how you can completely do a plant process design from scratch in Aspen HYSYS and with all the necessary basic building blocks. So we are almost finishing now. So let me just show you this. So this is a final flow sheet, which is the same as what we did. And further resources, where do we want to learn more if we are thinking of like learning more things? If you want to learn more about HYSYS. The first book I recommend is Chemical Engineering Process Simulation by Professor Dominic Fu. So before you go into HYSYS, make sure you know the basics, which is in this book, and I recommend this book for the basics. You can also look at this free book by engineer Muhammad Kamaruddin Abdul Hamid, HYSYS, An Introduction to Chemical Engineering Simulation. And because this book is free, so I recommend that. And it's actually done by a UTM lecturer. And the third recommendation will be Juma Haidawi, Chemical Process Design Simulation, Aspen Plus and HYSYS applications. It goes into very a lot of detail, which is sometimes too much detail. But the good thing is that it compares between Aspen Plus and Aspen HYSYS, so that if you have if you are trying to compare two different softwares, then you know how to do the same thing in these two different softwares. On aspentech's official website, you can get official kind of like courses. You can apply for certification exam, but they are not cheap. The official price for aspentech HYSYS course is like $1,500 or $2,000. The exam is about $150, so it's not cheap. So usually I won't go for that. I just read books and then try out my HYSYS. And the last tip I'll share about today is caveat emptor, which means that buyers beware. There are a lot of people out there offering like courses for HYSYS, and so sometimes they charge a lot. But you just have to beware of scam tutors, whether they actually are real tutors or they just take money and run. There are a lot of people out there, especially after COVID, when a lot of people go on for online learning. One very good tutor that I recommend is Jefferson Costa. He's a Brazilian, and he has a YouTube channel called Jefferson Costa Chemical Process Engineer. You can search for it, and you can watch. He makes a lot of HYSYS videos. And you can also join my group if you haven't. It's in Facebook and Telegram, where I sometimes people share things about HYSYS in our group as well. So finally, just a final note for all people trying to start a simulation. I read the best advice from someone, which I will share in my LinkedIn post here. It's called the 10 Commandments of Process Simulation. The 10 Commandments of Process Simulation, which is simple things that you need to know before you start doing process simulation. The first is understand your objective, as I mentioned at the start. Identify system or process, as I mentioned at the start. Imagine what's going on physically, also I mentioned at the start. Identify mathematical models. Know components. Know the context of bit streams, for example, whether they are gas, liquid, mixture, solid, whatever. Know your components boiling point so that you know what to set as a light key in a distillation column, what to set as a heavy key in your distillation column, how to arrange your distillation column, what products you put on the top. So logically, in the distillation column, the lightest boiling point always puts on the top. If you try to set it the opposite way, Aspen HYSYS will throw an error. Keep track of the unit of measure. Unit is very, very important, especially in reactor sizing. Putting in the wrong weight, for example, kilomole instead of mole, will cause your reactor size to increase by 1,000 times or decrease by 1,000 times. So if I calculate your reactor size is 0.003 meter cube, then you're like, 0.003 meter cube is small. Or you might calculate the reactor size as 1 million meter cube, and then you're wondering what happened. Usually it's a unit is wrong. You forgot to convert a unit. Number 9, always do a simple material energy balance first to make sure that your input is correct and logical. Because the simulator will not differentiate whether your input is logical or not. It will try its best to calculate. Then if it cannot, it will just give an error and you don't know what the error is for. Finally, plot the phase envelope for important streams. For important streams, it's good to know where the stream turns into gas, where the stream turns into liquid, where the stream turns into solid. And that's why I show you the built-in phase diagram that you can see, okay, halfway my increased temperature, it actually turns into gas, and so the pump doesn't accept that as a valid input stream anymore. My last term here will be, if you fail to plan, you plan to fail, simple as that. So make sure that you go into a process simulation job or process simulation task well prepared. Make sure what you're doing it for, and you make sure that you know the system and its fixed before you go in, and instead of just going in blind, you try an error and then you get frustrated by a lot of different errors. Okay, so I think I'll just end here. This is my email address, my LinkedIn profile if you'd like to connect. And I'll just open if there are any final questions that you might have in this session.
All right, thank you, Mr. Teo, for the sharing about Aspen HYSYS. So, okay, so far we have no question in our chat box. All right. So I think while waiting for the participants to pause, if you have any question, to pause in the chat box. So why not we have the photo session now? So now I would like to invite all participants to switch on your webcam for the photo session. You may apply the virtual background that is available in the chat box. We will wait for 2 minutes for everyone to get ready. Thank you. If you are ready, please switch on your webcam to have a photo together. All right, so far we have a few to open.
Okay, I got my background up. So yeah.
All right, thank you. So if there's no more people to open cam, perhaps we can have the photo right now. We will take total 2 photos. The first one will be the formal one, and the second will be a freestyle one. Okay, so let's take our first picture. 3, 2, 1. Okay. So the second photo will be a freestyle. So feel free to have your freestyle photo. Okay. 3, 2, 1. All right. Thank you. So thank you, everyone. All right. So thank you so much for your cooperation. Next, we will share with you the link to the feedback form. You may scan the QR code on the screen or click the feedback form link in the chat box. Your feedback is highly important for our continuous improvement. Thank you. All right. So, ladies and gentlemen, this marks the end of our Aspen HYSYS workshop. On behalf of the organizing committees, I would like to thank you again for I hope that everyone who joined today gained more than they expected from the session. Thank you for attending, and I wish everyone a lovely day ahead. Thank you so much again, and you may all leave the meeting now. Thank you.
All right, thank you for joining, and thank you, UDP, for hosting me. See you guys next time.
Bye-bye. Thank you.
Thank you so much.